Good evening, good evening. Rangappa will start.
A very warm afternoon to one and all present here. I would like to extend my heartiest gratitude to everybody for joining us today for today's Quantum Ray Symposium. Today we shall be focusing on quantum rays. Before we start the session, let me take a moment and welcome everybody. So first and foremost, I would like to welcome Dr. Deepa Shenoy, the chair of IEEE Bangalore section, to address the gathering.
Thank you. Shall I start?
Yes, ma'am.
Okay. Good afternoon and warm welcome to the first symposium on quantum rays. We have 3 more in the series: drone computing on 30th July, digital reality on 24th September, cyber physical system on 26th November. And the format of these symposiums will be usually will be conducted in the evening, Saturday evening from 4 to 8 p.m. With a mix of academic and industry speakers. And Saturday evening is a comfortable time to attend without sacrificing much of family time. So IEEE Bangalore section is a vibrant section with around 7,900 plus members, third largest section in the country, in the world, with a large number of dedicated volunteers. Some of the other flagship events are Connect conference to be held from July 8th to 9th, conducted in hybrid mode. And last date for paper submission is just 2 days away, that is April 11th. To encourage UG, PG and PhD students, registration amount is kept as low as 2,500 with various types of discounts. So don't miss the opportunity. We also have our BHTC and BTC conferences in the month of October and November respectively. So let us all come together to make this event successful. Thank you so much for inviting me. All the best for the symposium. Thank you so much.
Next, we would like to invite Mr. B.S. Bindu Madhava to address the gathering, the past chair of the IEEE Bangalore section.
Good evening all, and welcome to this particular symposium on quantum rays. This is the second edition of the thing, what is happening. This is in line with the IEEE quantum in global, and in that particular lines, we wanted to conduct symposiums. As a part of that, this is the second edition, and I think if most of you are involved in quantum computing space, it is known that there is a lot of emphasis given for building the compute hardware in space of quantum. But it is equally important that we have the innovative quantum algorithms and also the basic control softwares which are in this particular space. Just to give a feel for the thing, the quantum stack, which consists of 7 layers, that's how it is being defined. So we felt that the software component becomes very important in this space. because other than the qubit realization, how it is done, the whole thing depends on the electronics and the software which runs that particular thing, and also the applications which are on the uh, application software also becomes important. So if you see, the quantum stack is split into 7 layers. The bottommost layer, of course, without the quantum hardware, we can have some simulators being there, where which we can use for some verification, validation of the performance. We can model the thing and use the simulator. So there are plenty of simulators which are available in the market. So the first layer is the quantum plane. The quantum plane basically talks about very close to the quantum qubit realization area, where in native gates, connectivity, and interconnects. So these are some of the things which fall into the quantum plane layer. Then the next layer is the control plane, where the control plane talks about the crosstalks and wiring integration and heat management. Because if you go to
Sorry to interrupt. Would you be sharing any slides, sir?
no.
Okay, all right.
I just thought. Okay, so basically the control plane basically constitutes of the crosstalk wiring or the integration components, and also the management, where there is different types of realizations being taking place. The other thing is very close to these physical things. There is something called as control logic uh, layer. The control logic layer basically handles the pulse and timing calibration and optimal controls. And basically, this is where we will be able to sort of realize the qubits, where we move from one qubit to whatever the qubits today we are talking about. So the realization mainly it depends on this particular thing, and there will be a lot of drivers and softwares. The other thing, other layer is the architectural layer, where the architecture, that is where the quantum processor unit will be there, and the kernel becomes important there. Of course, how you handle the error, especially in the noisy environment, that is where the quantum error corrections takes place in this particular area. And of course, there's something called as magic state factories. These are nothing but the components which are to be realized, different qubit realizations. And the QRAM also is another area. The and we'll have the classical.
Now your audio is getting cut off.
Sir, no audio is coming, sir.
Hello.
Yeah, we can hear you now, sir. Yeah.
Not audible again.
Am I audible now?
Yes, sir.
Yes, sir, we can hear you. Yep.
I think I have logged in another device.
Okay.
Oh, it's
Yeah.
clear now.
Yeah, we can hear you. Yeah.
Okay. So the other layer, what we are talking about in the quantum stack is the applications. So the application is basically the in the area of machine learning and other complex problems to be solved. So there'll be a lot of development management tools as well as work management workflow management tools also has to come into the picture. Keeping this as a base, so we have structured this particular today's conference, symposium, such a way that there'll be a talk from the IEEE Quantum Global representative, who's a steering committee member. So we'll be talking about what is the thing happening at global level. And then subsequently, we have got speakers who will be talking on what is the future directions of quantum, especially where AWS will be representative will be talking. And like I told in the framework, the algorithm also becomes important. So Professor Manish will be talking about the algorithmic level, how the things are handled. These days, the symposium conferences doesn't end without using the word artificial intelligence. So there is a talk on quantum for artificial intelligence, that is AI, as well as AI for quantum. So it's a sort of a thing what we have to watch out, how this quantum becomes important, right? And then subsequently in the simulation space, there is one good talk which is talking about the prospective applications, and also at the gate level, how the simulations can be done easily, and how you can play around at the gate level simulation. So I think this is how the symposium has been structured, and I wish all the participants good learning in this particular space. And I thank the organizers for giving this opportunity. Thank you.
Thank you, sir. So now we would like to invite Mr. Sachin Punyani, Chief Technologist and Lead Architect from Amazon Internet Services, to address the gathering.
Thanks. Thank you very much, sir. So can I share my screen as well?
Yes, sir.
Yeah, you can.
Can you see my screen?
Yeah, we can. Yes.
Thank you. Thank you very much, sir, actually, for setting up the base on the 7 layers that you shared. So we'll be majorly focusing on the quantum applications and how exactly are they being used, or how people are looking at using those applications in the real business scenario. So you touched upon the hardware part, you did touch upon the other aspects of the quantum stack, but we'll be focusing on this area so that people know that what is in quantum applications or in quantum computing in the immediate or near future, basically. So we'll try to give a small overview of that. So just before getting into the deeper aspect, see why exactly people are looking out to the quantum computers. It's a common point that we are going to make, probably all of you are aware of. There are certain problems in the classical compute scenario which might take a huge time to compute, maybe hundreds of years, even thousands of years. and the way quantum ecosystem, the entire stack is being built, it can address those problems much faster. It can happen that the problem that is being solved in the classical computers with a proper algorithmic way is being solved, can be solved by the quantum computer in minutes only. If the classical computer algorithm, some recursive algorithm, some reiterative algorithm is taking hundreds of years, requires huge compute cluster capacity, huge RAM, quantum computers might be able to solve those particular problems. But we need to identify here that we are not talking about doing the 2 plus 2 here, or we are not talking about setting up our web servers, application servers, database servers. Quantum computer, as on date, the quantum applications and the entire stack is focusing on some typical type of problems only. So just starting, what are the potential applications? If you look, it is covering almost all the industry areas. Logistic, we are talking about traffic routing, network optimization. In the finance, we are talking about portfolio selection, risk management. In agriculture, also about the manufacturing the fertilizers with the less energy. In the if you go into the chemistry space, which is not highlighted here, finding the right combination of the new drug faster. So, and machine learning as well. So if you look at all those problems, which are towards the industry, majority of them as on date are the problems which are optimization problems. Many of them actually many of them do not have their precise algorithm in the classical world. Many, and they are people are implementing those algorithms with the help of heuristics basically. If you look at all those problems, if you keep on adding the constraints on those optimization, if we talk about traffic routing, for example, you see that uh, what weight are the ships going to carry? What route should they take to minimize the cost, minimize the time? Now, this is one problem. Now, it might happen that these ships are carrying something perishable. Now, how should they go so that the items that they're carrying should be delivered in such a way that they do not perish? So every industry, every shipment will have its own requirement. So the problem definition changes, but effectively what you're trying to do is either maximize or minimize some function. So quantum computers can solve those kind of problems much faster, much more in much more better way. Machine learning inherently is an optimization problem. We try to optimize the objective function. So this is an initial set of the problem that people are trying to target. Take the example of the security, cyber security. We know the passwords are encrypted. The cryptography is done with the help of two large prime. The basis is that there are two large prime numbers. They are multiplied, a large output is attained, and then some operations are performed. Now, if you want to decrypt those things, it is really difficult, because finding a prime factor of a exponentially large number is difficult. But if you define the problem properly, it's easier to do with the help of quantum computers. So those kind of problems quantum computers are trying to solve. Just going a little deep, actually, the traveling salesman problem is a NP hard problem. We just are supposed to find out the possible route where each city is traversed once. But if you see in the classical compute scenario, it is an NP hard problem. But with the quantum computers, people have tried to solve this problem with the help of quantum annealers. So I'm not touching the hardware part here, but we know that there are two different programmatic or application development approaches. So one of them is annealing. So people have been able to focus on this problem with the help of D-wave annealers. If you look the problems, see again the optimization problem, job shop scheduling, find the right schedule. Every organization, every industry use case will have a different constraint. So if you look at the constraints at the bottom of the slide, it says here it has been assumed. I mean, in the example, I've just taken that example from GitHub. Actually, you can refer to the example there, that how it has been implemented. But each task starts only once. But there might be some other organization where they can restart the tasks, where they can run the tasks in parallel. So all those constraints, if you know for your particular problem, you can define the problem in such a way that you leverage the quantum computers to solve those things. So I'm just trying to take the quantum computers closer to the industry problem, taking couple of more examples. In the shipment industry, we did talk about delivery, but how to pack the shipment. In the e-commerce industry, if you see, it's a very common problem that you are ordering multiple boxes, multiple items. How should these items be packed so that They come in a container with least cost, least weight, should be easy to carry. So again, different constraints of a different organization, but it's a typical optimization problem. In any optimization problem, as you keep on adding more constraints, more difficult it is to solve. And with large number of constraints, it becomes so the time taken by to solve the problem is so exponential that it cannot be solved algorithmically. Then people start finding the alternate routes of finding the heuristic based solution or something. But quantum computers, particularly annealers, can help you solve those problems. A very common problem you would have seen where different pathology labs have a challenge that the blood samples are being collected from different locations of patient, the home collection of the blood samples, but they should be taken back to the same central lab where the testing is being done. So they also have their own constraint that blood sample should not be held for a longer period of time to avoid any contamination. So again, if you see all optimization problems falling in different industry area. So when you are focusing on your problem, when you see these kind of problems with large constraints, you can clearly see that quantum computers can come to your rescue. And annealers have reached a stage where you can define the problem and try to solve the problems for the production use case as well. Then then we did decide that, okay, what we did understand that what are the problems that people are focusing on. Sir also shared one part of the stack that there is error correction and error detection. The challenge with the qubits or any quantum hardware today is that qubits are not very reliable, not very stable. If we talk about the classical bits 0 and 1, we know that there is a proper threshold beyond beyond that voltage threshold you have 1, below that 0, and that system is quite stable, quite accurate, kind of error free. Qubits are not error free. You'll see that people, different hardware vendors or different manufacturers of the quantum hardware, they talk about error rate between 0.1% to 0.5%. That 0.1 to 5% error rate can be very critical. So just taking ideas of few algorithms here or few approaches, we did talk about that finding the prime numbers of a very large exponential number. So the qubits, which are logical qubits or pure qubits, which are noise free, theoretically a Shor's algorithm can break the RSA algorithm with 6,000 qubits. But if you have just 0.1% error rate, to ensure that error is detected properly, corrected properly, and the output comes right, theoretically you need approximately 10 million qubits. So if you see that from 6,000 qubit requirements, it with just 0.1% error rate, it reaches 10 million qubits. So this is the challenge that we have right now, where entire industry is working on to improve the qubit reliability. So that is where so people have found out different ways of it. One, like developing better qubits, better hardware ecosystem. Second, finding better error algorithms. And then third is people have found some part of this solution in the form of annealing. So if you are trying to build some algorithm or application based on universal gate based scenario, applying typical vector or the matrix operations, then kind of you are setting up the circuit, and the chances of errors are higher. If the annealer system has predefined topology, D-Wave systems, if you talk about them, both the D-Wave systems, they follow a particular topology. Both of them have a separate Pegasus and Chimera topology, but if you look at them, they have a controlled topology, so the reliability of qubits increase. Second part that happens there is you can define your equations that you want to optimize that map to your business problem. Then instead of writing a large code with new quantum ecosystem or quantum hardware mindset with qubit mindset is not required. Once you have defined your equations properly, you can map them to the existing topology. So that becomes a much faster way of solving the problem. So people are finding out way that while the gate-based systems mature, the biggest gate-based system recently, one organization announced that 100 qubit plus system. While for this RSA, we are looking out for around 6,000 qubits to solve this problem. So requirement of qubits is too high. While industry is working on that part, certainly they'll be able to solve that problem in maybe 2-3 years, 4 years from now. But how to bring those quantum computers in the business scenario, So people are trying annealers if they can leverage to solve their business problems. So this is where we say that the current scenario is. So if you see, there are 3 stages, 1, 2, 3. So when the ideas of using quantum computers began, so people tried the quantum algorithms in the simulation on the classical computer. So they built the algorithms which were classically simulatable. Because this requires large amount of RAM. The qubit mechanism, quantum ecosystem or qubit state actually is representing large amount of data in itself. So simulating them required huge RAM, which was not possible. So if you look there in the original stage 1, there were very less number of qubits. Then the error rate of the qubits or the quality of the qubits was not so good. But effectively, if you see, this is where people are fighting for the quantum supremacy. I mean, they are trying to improve the quality. They are trying to improve the number of qubits. We see that we'll reach actually finally to that end goal. But I mean, by the time we reach, we are in this area and the applications currently are being built on this layer only. So that is where we call it as NISQ, noisy intermediate scale quantum. We know that qubits are noisy. We know we are right now at intermediate scale. Maybe 3 or 5 years from now, we'll be in a much better position. But when we already know that some of the problems for our business can be solved by some of the systems that are available, why not to leverage them? So that is where we just looked at some of the use cases that industry right now is targeting. Second point comes is, we do talk about quantum ecosystem, quantum computers, but how can they be brought into the industry solutions? The top layer, if you see here, it's machine learning. Just taking an analogy of machine learning with quantum computers, we know that all of our applications are on CPU based system, the classical CPU that we have. But we know that the kind of calculations we do, the kind of objective function calculations we do, GPUs are faster, more effective for those kind of problems. So the GPUs work as co-processors while CPUs work as main processor. They reside very close by, and CPU, I mean, if you have a problem, a typical iterative problem, you know that you do multiple epochs, multiple iterations in a machine learning program, then CPU sends the information to GPU, all calculations are done, then the output comes back. So this iteration continues. So GPU works in the co-processor mode. We also know that if you want to leverage QPU, our existing web applications, database ecosystems, all those will run on the classical ecosystem only. QPUs are meant for solving some particular type of problems. So why can't we offload them? So this is the second, the bottom layer that you see, that is, this is what people are trying to use to bring quantum computers to their real world application. So they have started building variational quantum systems. Again, annealers also allow taking the input parameters. So the applications run typically again on CPU. The information is passed on to QPU. The circuits are executed, the values are taken back. The difference between the top and the bottom layer is that in a GPU and CPU combination, both can reside on a same server on same motherboard. Because the technology has advanced to that level, both our chips can reside on same motherboard. While quantum computers are separate computers, so the communication happens over the network. So there are services, cloud services, there are, because quantum computers right now, people do not, I mean, they are not so prevalent that people are ordering the quantum computers from some organization and procuring in-house. They are available on a slot basis, on access from various organizations. So they are available through cloud as well. So there are cloud services that are making those quantum computers available, and then you can create this kind of scenario to bring the applications usage of quantum computers to the real world. So this is the current scenario. Now, because I come from the AWS side, so I'll just share that just try to bring some glimpse that how you can do all these things that we said that is happening in the industry on AWS. So this is where one more problem that is solved is, so because in cloud we have large number of services, 175 plus cloud services. So for traditional applications, people do talk about compute, storage, database, all those things, but there are large number of services. So one of those services, Amazon Bracket, which actually is giving access to quantum computers. Now, one more case, like we said, there are different people, so different organization. For example, D-Wave is designing annealers. They have two different annealing systems. INQ is a universal gate-based system. The underlying hardware technology is trapped ions. The Rigetti is again on superconducting mechanism, but universal gate-based. Now, point is, if you want to build some solution using these systems, then you need to download their SDK, build the program in that SDK, and then do. Now, today you have decided to build some application, for example, on INQ. Tomorrow you decide that, no, I want to run my circuit on Rigetti. It's a completely different exercise because you will have to download Rigetti SDK, build again. This is where cloud SDKs are coming into play. That bracket actually is giving access to 3 or 4 different systems. As time passes by, more will be added. But it also at the same time is giving a common layer of SDK. So if you are building a program in bracket SDK, you today decide to run on INQ. Tomorrow you say that I want to run on Rigetti, no code change, just shift and start running on Rigetti. So those kind of challenges are being addressed and solved by the cloud services. And of course, all other commercial aspects that we say that, okay, security and privacy, because you want to bring system to the real world application. So you might have security, compliance, all those challenges, requirements. So the cloud services are bringing in those kind of solutions there. So this is the role that is being played by the cloud services. And this is how it is happening. So if you want to submit some job to a quantum computer, you can decide that, okay, you have taken one SDK. Now from there, when you want to submit the execution, you can bring it to any of the hardwares. You can bring it to multiple simulators, different simulators available. So all of this comes under same SDK. So there is one layer basically. Plus, like we said, there are 175 plus services. Bracket being one of them. It is very well integrated with the other cloud services. So your compliance requirement, your procurement requirement for the business, they are all met. So storage integration, the monitoring notification integration, permissions, you want your data to be encrypted, so key management. So point here is cloud services now are bringing quantum computing to mainstream so that you can leverage them in your final applications. Effectively, you can leverage quantum computers as a co-processors only, and your existing applications are running on CPU based systems. Your enterprise application are web servers, database servers, different kind of applications. So they are your regular business applications. And in case you want to bring some optimization, some improvement in your processes, in your operations, data still resides on those existing applications, and you need to pass that data, you need to pass that operation to quantum computer to be done much faster. So this is what the cloud services are enabling right now. Again, solving again the business problem, we said, normally if you talk about the classical applications, people say that they want to build microservices, they want to build API based architecture. So this is where this kind of ecosystem comes in, that the quantum computing service, which is offering multiple quantum computers and simulators, can be connected with the other cloud service like the API gateway, so that you can build the APIs. Now, suppose you have built an algorithm, you want to expose that algorithm as an API. So that is possible in cloud. You want to control the API. You want to ensure that only relevant people do access. You want to monetize those APIs and want to track that who is accessing, how many APIs, user management through Cognito. So point here is the quantum computing is now part of cloud as a mainstream service. As the quantum ecosystem improves, of course, this more services, more benefits will be available, but whatever is available is now readily available through cloud to be integrated with your business applications. Same way, I mean, people plan to build the event driven applications as well. Depends what, and you want to connect the you want to connect it to the database, machine learning, analytics. You want to bring quantum into all other areas of the regular business applications. That is also possible. Sir also talked about the simulation. So this is where the option comes in, that you know that when you're building some machine learning code and you want to use quantum systems, so before you reach out to the quantum system, you would certainly want to try on the simulator. So different simulators offering different kind of qubits and different kind of simulation mechanism. again under the same umbrella. So it becomes much easier for you to build your code, test your code before you take it to the final world. And the local simulators as well. Local in the sense you can now just when you have the Bracket SDK on your laptop, you can simulate a quantum computer up to 25 qubits on your laptop itself or your desktop itself. So basically bringing that quantum computing scenario so that you can develop the code, test the code, everything on the on your laptop. So bringing quantum computer to your laptop so that you can easily develop and leverage in your business application. So all that ecosystem that is required to build a quantum computer based application, the cloud is trying to bring that to you. And just going in the end to touch that, there are open source frameworks now available which let you do machine learning on the quantum computer much faster, the PennyLane. So people have been doing machine learning using the TensorFlow, PyTorch, those kind of model frameworks. And PennyLane integrates with TensorFlow and PyTorch so that when your optimization requirement comes and you want to offload it to QPU, you can do that. TensorFlow has a facility, for example, that whether you want to do your model training on CPU or on GPU. Now, with the help of PennyLane, you can pass it on to the QPU as well. So this is the entire ecosystem built up for the applications that we discussed at the start of the presentation. So that's just wanted to give you a glimpse that this is how quantum computers actually are coming into the mainstream, what people are trying to do and how they're trying to do. So that's from my side.
Anything happening on the energy sector?
Yeah, so there are multiple use cases. If you see in the slide I tried to cover, there are multiple use cases on the energy sectors as well. People are trying to find out the materials for the carbon capture. People are trying to find out the mechanisms for cheaper solar cells. I mean, they're trying to optimize the power consumption. If you look at the data center scenario, I mean, if a large data center is there, then the power requirements are very high. So people, and there are multiple factors contributing to the energy consumption. So they are trying to see with the various factors that how should the energy consumption be optimized. So people are trying in that direction. Can't take the name here, but one of the large automobile companies trying to work on some scenarios that how to improve the fuel efficiency of the car. That is also an optimization problem. So people are looking at different scenarios. And when we say fuel efficiency, again, the same challenge, multiple constraints. So they are looking at the various aspects of engine. They are looking at various aerodynamics aspects of the car design, because there are multiple factors that that contribute to the fuel efficiency. So they are bringing in those parameters and trying to see that how fuel efficiency can be improved. So they are trying to solve that problem. They're looking into that.
Are there any other questions from the audience? Thank you so much, Mr. Sachin Punyani, for the informative session. I don't think there are any more questions from the audience, sir.
Sure. Thank you. Thank you very much.
Our next speaker is Mr. Nagendra Nagaraja, founder and CEO of QPI Technologies. Mr. Nagaraja has completed his bachelor's in engineering from Bangalore University from 1996 to 2000 and has further gone on to study at Illinois Institute of Technology for his master's and Indian Institute of Management, Bangalore. And after that, he has studied at Coventry University. We welcome you, sir.
Yeah, thanks. Thanks a lot for a brief introduction. So let me share my screen. So today we're going to touch on the topic of AI for quantum for AI. It's a very interesting topic what company is working on. Okay. So thanks for this opportunity to talk to you, and I'm also mentioning my colleague's name who contributed for this PPT. So it's very interesting that these two sciences, quantum and AI, they are actually very much it will get co-integrated. And as a company, Occupy AI, we are vertically integrating all the solutions with AI and quantum. There is no product what we have which is standalone AI or quantum. It's always it contains both of them. Okay, so as a company, I'll just introduce what we are doing. We are a quantum and AI company, one of its kind of a startup which has both quantum and AI, and we are actually using AI to actually control the quantum hardware, and in turn, we are trying to actually make sure that the model what we develop in AI that use a quantum technology both for computing as well as modeling. Okay, so we're changing both compute and modeling using both quantum and AI. What we say as the future of modeling will be combination of bits, qubits, and neurons. And then for accelerating this, we do require quantum compute because the kind of optimization that is required to search the model, search itself, that can be put on a quantum computer. And also in future, if I need to really model the intelligence, we can use qubits in a better way. Okay, so this is a brief introduction of what we are doing, and I'm just going through the quantum basics just for novice. This is how quantum computer looks, and usually the bits are represented like this, and the qubits are this, which can really encode more information. And if you can control this data structure, the qubits, you have a quantum computer. It's not just you have a qubits and you have quantum computer. You need to be able to control these qubits, and then only as a computational element, then only you can get quantum computer. And the other thing is quantum mechanics. I did not go into detail, but basis of quantum computing is quantum mechanics. Basically, when we apply quantum mechanics to computation, we get quantum computer. Either it can be superposition, or it can be entanglement or interference. So it's all the quantum mechanics principle. So this is on the superposition side when we have a photonic superposition, and this is where quantum power lies in the principle of superposition, and the way we can actually use the superposition to apply for a computation that gives us the reason why it is very much efficient in terms of optimization and search is because of the superposition theorem. And other is the biggest problem we have in quantum computer is a decoherence, very short decoherence time, and that is something is an engineering problem that we need to solve to make quantum computing more efficient. So what happens in quantum computing is if it has to be longer in the superposition time, superposition state, then we can exploit quantum computing. But if it loses its coherence and it collapses, superposition collapses, then it will not be no use. Okay, so the biggest thing that hardware engineers are doing right now is how do we actually make sure we have a long coherence time, okay? The T2 time of the quantum computer. And about the other property of quantum computing is entanglement, where when we have two of this compute element, either it can be photons or it can be a spin or it can be a charge. If they're separated longer anywhere in the world or anywhere in the universe, they are entangled, and that we need to have more and more qubits which are entangled to make this quantum computing more powerful. And this is one of the experiment where we really look into we really can produce entanglement of photons. And then you have other important property of quantum computing is quantum teleportation that depends on entanglement. And this is a far off thing. We're not trying a lot of active research are going on in quantum teleportation, but still, if you look at the way we can apply to communication or way we can apply to computation, it's still far off. It's not in the near term kind of thing, but it's a very important area of research. If somebody want to take up a research or start a PhD, I think teleportation is one of the good topic to do. And then superdense coding. We can do a superdense coding using qubits, and that is really good for actually the information processing, the way we can actually really code the qubits and I mean, if you want to store, if you have a quantum memory or if you want to have a quantum communication, super dense coding will be very good, of a very good use. Now, this is an important theorem what we have in quantum computing. Every quantum computer actually has to be based on this theorem, Differences of criteria. So basically, as I go to explain about different type of qubits, we depend on these things. We have a universal gates. It has to be implemented in the quantum computer. If you want to really have universal quantum compute, then you have to have a universal gate implemented. It has to be scalable with well-characterized qubits. It should be able to be initialized, and decoherence time should be longer than the gate operations time, and they should be read out. I'm just going to explain how we are exactly using AI here for actually tuning the qubits, and then interconversion of stationary and flying qubits. It's very, very important here, and faithful transmission of the flying qubits between specified location. So this is one of the basic theory where we can build a universal quantum compute. I know we have annealers, but annealers are very much limited. Okay, and although we are solving some of the near-term problem, there are digital annealers which can outperform the quantum annealers. Okay, and there are some part of AI which can do much better than quantum annealers. Okay, like you have a graph neural network. So we have simulated million variables using graph neural network, but real quantum power is really in universal quantum compute, the gate-based one, where we can implement universal gates. So these are the different physical implementation of qubits we can have. We have a variety of them which we can implement. As a company, we are implementing superconducting qubits for a test bed, and we are doing a lot of research on spin qubits. Our aim is actually to take it to 2000 qubits, 2000 logical qubits. That can be millions of physical qubits here. And we currently have, in India, we have most powerful quantum computer here with 25 qubits. We are forming a test bed with 3 of the test beds open for research and even the ecosystem to actually access. And it's all based on semiconducting loops. Okay, these are semiconductor qubits what we have implemented. But there are other qubits like trapped ions and topological qubits, which Microsoft is working on, of course, diamond vacancies. But we feel that semiconductor qubits are more scalable because you can implement a lot of them. If you can implement 10 and you figure out how to really get a quality qubits or a big quantum volume, so we can scale it. That's what we are dependent on. And superconducting qubits are where the large quantum volume quantum qubits are there today. Of course, ion traps has a larger quantum volume, and this is like a little bit old. This is gone long way from this presentation. Okay, and the thing is, we should have a system to, as AWS has implemented in the bracket, we should have a system to actually exploit all these qubits depending on their progress, and that's our principle also. So if you look at, I'll come to our hardware setup, why we are using AI for quantum and quantum for AI. So that's where we are actually forming the support for universal quantum qubits, all kind of qubits. And of course, the quantum qubits are prone to error, and there are different kinds of error that can happen. There are 5 different kinds of errors we figured out, and that requires error correction. And quantum error correction is itself a deeper topic. And nowadays, I think noisy intermediate scales quantum processor can be integrated into the classical one, and we can exploit it as long as we can correct the error. Okay, and mostly these are smaller errors, smaller kind of error, like we can correct first 3 errors. Okay, still decoherence time, correction of decoherence time. There are research on the surface codes, and there are research on new kind of error codes that can be used for actually increasing the coherence time. And this is typically the way the quantum errors. It's not much different from channel error correction and coding. It's similar to that. Only thing is special element here is in channel error correction, you have communication channel, you have AWGN noise or some noise actually inserted in the channel. But here it's an interaction between the classical and quantum world that creates a noise. Okay, and there are different codes, repetition codes, and then there are stabilizer codes, CSS, and quantum block codes, and then quantum convolution codes. But I think the surface code is one that can actually play important role, but such is still very nascent there. It is not really matured enough, and we not got any concrete results on this because we don't have a large number of physical qubits that is implemented. That's the reason I think even the channel correction physically has to be proven, or even like put it onto the field. Those kind of results are not yet available yet. And what can we do with quantum? I think if you have 2000 qubits machine, which is not a NISC, but it is really a universal quantum computer. I think this is the power of quantum computing. Basically, you can break, 2048 RSA encryption within 10 seconds, whereas a classical one can require until 317 billion years. Okay, and all this, quantum easy algorithm today it is tough with the classical word and providing us a lot of security, but this will all be broken once you have 2K of logical qubits. That means that millions of physical qubits what we require. And the Grover's algorithm for the search, again, I was saying that we are using this AI modeling, and there we have to, what we have is an AutoML system, automatically come up with the model through when we have a large amount of data. And for that, we do require some kind of a Grover search that we are doing, which is our patented one. And there, if I can have 1000 to 1000 qubits, I think the Grover search will be very powerful, and we can speed up the AI modeling with that. So that's one of the thing, and this search algorithm can be used for many other applications. It can be a materials, it can be drug discovery, or it can be kind of a data search. Okay, so again, this is this can be enabled once we have more than 1000 qubits, 1000 logical qubits. So some of the things what happened in the quantum world is like we have this kind of applications. We have the technologies for applying to different application. For example, amplitude amplification can be used for unordered search, graph and network properties, data collision algorithms, and matrix product verification. And then phase estimation is there for factoring quantum chemistry. Phase estimation alone, if we can get it on 1000 qubits, we can solve a lot of things in quantum chemistry. And then we can also do it in the factoring. And apart from this, we have quantum walk, and some of the material simulation is based on Hamiltonian simulation. These are the technologies which can be applied when we have universal quantum gates. A lot of things cannot be done on annulus. Okay, so I understand that you can do a QUBO with annular, quadratic and constrained binary optimization, but these other algorithms really require universal quantum gates. So just to explain what happens with NISC devices, I will just give an analogy. This is a fort, and this is where we have a fortress of fault tolerant system, quantum system, and this is our plane, which is really of noisy, and is all classical word. So once you cross over from here to here, it's all classical word. Okay, but the real thing is the interaction between these two words. You have to cross this plane which has a noise. Okay, so then this has to be covered by this magic mode of error correction. It's very, very important. It's a very nice analogy here. Like this mode is what makes really quantum compute fault tolerant. Okay. So these are some numbers of qubits. So anything that is less than 1000 qubits, we call NISC. Anything more than 1000, it is universal quantum compute. Really at 2000, we have a lot of application. And this is a principle where the way we can design the system, hybrid quantum classical architecture, where we have the quantum circuit and circuit partition into quantum and classical, and then we have a quantum processor, and we combine the measurement using classical processor. So there is no way that today we can have a standalone quantum processor. It always has to interact with the classical processor. And most system in this world is mostly hybrid. For a long time, we'll have the system has to be hybrid. So these are some of the applications. Here is like a near-term application, okay, and this is a longer term and their impact. Okay, for example, drug discovery has huge impact, but it takes long time. It's a very, very long time. And the chemistry and molecular discovery can be done now, and it has a very high impact. Okay, so basically, this is where we see the commercial opportunities now. Like for example, once we cross over this curve of the impact and then the kind of applications we have. So this is where we are seeing a lot of opportunity, and it takes. Currently, we are here. Maybe in 3 years' time, most of this will be taken out. Okay. Even if you have 500 qubits, logical qubits with high quantum volume, we can do all those things. Okay. But this takes a lot of time. Like for example, drug discovery, I think it cannot be done with only quantum. I think a combination of the AI and quantum is a way to go in a drug discovery, and that should yield us some results. And biggest application of quantum computing will be in the finance. Okay, for example, optimization, portfolio optimization, risk profiling. These are the things that can be done very soon, not in the near, far future. So now coming to the topic of AI for quantum and quantum for AI. So this is what we are doing at our labs. So this is a spin qubit, which is based on silicon. The reason why we choose is it's very, very scalable. This is one physical qubit, but if I want to have an error tolerant qubit, I need to combine them to a logical qubit. So like 100 of them will give us one logical qubit, 100 physical qubit will give us one logical qubit. And this has to be tuned and controlled by AI. See, it's like analogy of this. If I have a 100 qubit machine, it's as powerful as supercomputer. And if I want to control that, it's not possible with human. It has to be done by AI. And controlling these qubits and tuning and reading out in microseconds or maybe like nanoseconds of latency, I think you do require AI for that, and that's a very big thing here. So this is our 3-chip solution. 2 of this will be available very soon, and in India we are forming 25 qubit testbed, which is the highest qubit count in India, and so we have a lab where we are opening up to our ecosystem, and also this will be our research lab for scaling it up to 2000 qubits. And the special thing about this is a classical chip, which is a universal optimizer chip. We're knocking out GPUs here, and we're forming these 3-chip solutions. Once our people start using this, it's very easy for them to replace any kind of qubits. And this control circuit also, like it's a universal control circuit which can support any kind of qubits, and it can scale up to around 5K or 6K qubits. But even the smallest of this control circuit is 128 qubit control, and we are one of the companies in the world, one of the few companies in the world which is making this control circuit. And this year we are taping it out, and the lab, it will be in the lab. So this is a platform we have, which will all be this education platform for quantum and AI. So this is a Pro, which is a platform for AI, but very soon we are going to deploy a quantum computer support for this. And our progression is entire intelligence modeling has to move towards combining quantum and AI, and that's a roadmap what we have. And this is a stack, quantum stack. And what it has is, if you look at this is an application layer, platform as a service, and these are different quantum application algorithms. This will be available as a library for application developer. And beneath this is where the really hard science is. Like you have a classical compiler and the classical computing and the quantum compiler, and then you need to have a control pulse generator, which is RF control pulses, so that you can control the quantum computing. So this is a complete stack which our software tool is based on. And some of the near-term application we can address is this. And also, like, we can map an entire neural network on gates. And that's the reason we say that quantum computing is very good for implementing neural networks. So let me introduce our quantum lab here where we use AI. So basically, this is a stack. This is how the quantum lab looks like, our quantum lab. So basically, when we generate this quantum control circuit, and when we have this quantum system manager, we will have a huge ML library to control these pulses, to control the qubits. So this is not be easy because you have to you have to optimize on the graph, on the response times, and how exactly you can tune the qubits. lot of hyperparameters you have to tune, and that is just not possible by manual effort. You have to use ML libraries to tune this. And we have a complete software suite here, which is QPyML, and QPyOpt is based on quantum inspired solution, which can use GPU, or it can use actually the quantum annealer as well. And we have a quantum QPySim, which is a simulator which can use pretty much quantum as well as classical hardware. So these algorithms today are optimized to run on our quantum circuit generator and quantum system manager, and we use a lot of this AI to control this qubits here. And this is giving us a very optimal results. Even with 20 qubits, I think we can do pretty much 25 qubits. We can do pretty much a lot of things here. And then when we have 2000 qubits, we just need to replace this, and we are all set to go. I think entire application stack is ready for us. And this is our quantum circuit simulator through which we can pretty much do most of the circuits, and we can have a Bloss-Spear simulation as well as tetrahedron for entanglement. And we also have a some of the maps, some of the analytics which we are integrating in AI, which can show us the different behavior of different qubit types. And we can also suggest user of this to use a particular type of qubit for their application based on this analytics. And this is where another area where AI is helping really select the best quantum computing or best quantum topology possible. So again, this is a real circuit, but we have logical part of this. Basically, we have a typical analog and RF circuit, and we have a readout and read-in, and then we have control, and we have finally a superconducting qubits. So as you see that this work on different temperatures. Our entire control electronics here is in room temperature today, but we are going to put it into the 4K arena. This we are going to collapse everything to 4K, so that we can make entire quantum compute setup simpler. And the way we control is these are the analog radio pulses, and this is controlled by our ML library. The way we tune and rate tune, and once we see that the performance degrading, it automatically retunes the qubits. And this is the entire box what we have. This is all fitted in the box, and typically we support most of the qubit types here. And our this has an ARM processor where our ARM processor and a GPU where our AI libraries run, and that will generate our control and readout. And these are some of the parameters measured to our box QPySense. This is actually commercially sampling now, and we are using in our lab, and we want to really also support a lot of systems which are coming up in India where they want the control and readout, and they have some 1 or 2 qubits. But this will be tested for 25 qubits this year, and then the plan is that the same hardware will be used to test 2K logical qubits, not physical, logical qubits. And by the time we actually reach a higher number of qubits, we will be actually upgrading our ML library, and our software stack will be very robust. And this is typical. This is a hardware what we have. This is a Xilinx board, and we have our add-on hardware here to control the qubits. And very soon we have qubits in India in the lab, and also dilution fridge. And typically entire stack is complete. So this is a logical representation of the way different temperature works. I just showed you first diagram of a quantum computer, and that's exactly what we are implementing. But the good thing about us is like we just need a qubit, and all the control logic and AI libraries are in room temperature. And this particular the hardware, one of the good thing is that we can do the cross optimization of different channels using AI. That's one of the patents what we have, where the readout and the control can be very much controlled through deep learning networks and ML libraries. So this is again the way we can put up this lab with the software interface. This will be running on our cloud, QPy cloud, and the hardware is in our labs. And then typically one can enter different programs through Jupyter Notebook or Python APIs. They can consume the Python APIs, or they can start programming on Jupyter Notebook. And typically, they can even model different, quantum applications or even AI applications on this. And then all these things work on the room temperature, and it has a connectivity to the lab, which is in the cryogenics, that is in the 10 millikelvin kind of range. And this shows like the dependency of quantum computer with AI, because unless we have this ML libraries here, which is completely tuned for the qubits, we will not get the noise level we want and the underperformance we want. And this is one of the most important application that we get ML libraries right. If you can't really control the tune the qubits, then it's very difficult to get the performance. As previous this particular noise reduction is very important, and ML can play a real role in actually this noise reduction. And this is our lab setup, what we have. And then after this, we can develop a native application here, or our own platform will be running on this. So we will enable a user to use QPy-AML or opt or sim, and they just start licensing this application, and entire these things will be transparent to them. Say, for example, if they want to do a route optimization, they use QPy opt, or they want to actually do the material discovery. We ourselves are using this for a battery discovery and as well as a superconductor discovery. We're a group of 5 companies, and 2 of them are in deep into materials. We are using QPy opt for actually come up with a new battery material, electrolytes, and then we are using QPy sim for some energy simulation. So this are all completely abstracted out. So user can just start on the day one with everything integrated for them, and they can just go on to writing their own application. And again, this is only possible live, real time, when we have those AI libraries completely optimized for controlling the qubits. And that's the power of AI. Yeah, thank you. Any questions I would like to answer now?
Yes, Nagendra, we do have a couple of questions from our participants.
Please.
Mr. Divakar wants to know any chance of quantum errors within decoherence time?
Oh, I think we have within decoherence time, of course, we will have quantum errors, because there are 4 or 5 types of error I mentioned. One is a readout error. Even if the coherence time, it is in the decoherence time itself, because of the readout error, we'll get errors because of readout, problem with readout, right? And it can be because even though the quantum qubits are in quantum the state superposition state, still we have it is in a decoherence time, but still we have things like when we read out, it can actually insert error. And there are errors because of magnetic interference, because we are working on spin qubits where we have to put the magnet, and even though it is in a valid T2 time, still because of magnetic interference. See, we are, I'll give you an example. We are doing the lab near aerospaces. That's where we thought we'll do. And if you have a plane flying and there is a radar, and that can interact with our lab setup if you don't do shielding properly in our labs, and that can interact, and that will insert a noise, and that will be an error for us. Okay. And we have to master in a way that the way we can read out very reliably, even if it is the coherence time is longer, still we can have a problem with readout. Yes, it's possible.
Thank you for that response. I hope that helps. So the another question is also from Mr. Divakar. As you mentioned about moving to control logic to 4K range, he wants to understand the advantage of this.
Okay, so let me share the screen. I'll just answer this question thoroughly. Very good question. Okay.
Sure. Yeah.
So basically, if you look at the, I'll just explain this this diagram. You see this. We want the control logic here, because otherwise, what happens is your quantum chip is here, and what we are assuming is that 1000 wire going outside this to control control circuit, right? You have the RF lanes, and then you have lanes for the power and all those things. So the wiring will be reduced and it will become very compact. So once we move the control, the room temperature control to 4K, this all fits in here. The control chip is here, right? And what happens here is, as I told this, currently today what we have is, today the setup is this. Today in our labs the setup is this. So basically, yeah. So basically, this is under room temperature, and there's a lot of wiring here for cryogenic. This is basically connecting directly to the qubit. Control is here. So, but where we want to be there in next year or so is, this control chip has to be in a 4K, and what we need to have here is a classical CPU. That's about it. This entire thing has to be in a dilution refrigerator. And when we do that, the wiring is less, and we get more reliability here. Okay, we'll see. If you have a lot of wiring and it has to travel the temperature, right? Definitely the reliability is low, right? And if you put everything nearby, the reliability of your entire system is high, and also it will be very compact, and it will be for example, this is just a lab. Okay, so assume that I want to implement hybrid classical quantum data center. I want to actually put the hundreds of this in the data center. We reach maybe 500 qubits, and I want to implement tens of this system, right? So the wiring it makes it very impractical to scale. When actually we put the control chip in the fridge itself, the wiring is very less. And as a company, we have a roadmap to make it all optical. Okay, wiring between this and this should be optical. It's not be electrical. And we want to reduce anything electric. This is RF and this is optical. Okay. So in that way, putting the control chip in the fridge itself will give us a lot of advantage in scalability.
Are there any more questions from the audience?
Yeah, Pranit, I think there are no more questions. We can move ahead.
Yes, sir. Thank you so much, sir, for the informative session.
Thanks for the opportunity to talk to you. Thanks a lot.
Thank you, sir. Our next speaker is Mr. Manish Kumar, who is an associate professor of MS Ramaiah Institute of Technology. Manish Kumar holds a PhD in computer science from Bangalore University, and he is now working as an assistant professor in the Department of Computer Applications, MS Ramaiah Institute of Technology. His area of specialization is information security and digital forensics. He has many research papers on his credit published in reputed conferences and journals. Apart from academia, he is actively involved in research and consultancy. He regularly delivers hands-on workshops, technical talks, and training for engineering institutions and researchers, faculty members, law enforcement agencies, and judiciary. He is a technical expert member in various committees formed by Karnataka state government for establishing the cyber forensics labs for the law enforcement agencies. He is a life member of the Computer Society of India, CSI, the Indian Society for Technical Education, ISTE, Indian Science Congress Association, ISCA, and a member of International Associations of Engineers, IAE, and ACM. We welcome you, sir.
Thank you. I'm audible? I'm audible?
Yes, sir.
Yes,
Thank
yes.
you. Thank you. Good evening, everybody. I'll just share my PPT first. Is it visible now?
Yes, sir.
Yes, we can see it. Yeah.
Yeah. Good evening, all of you.
Would you mind putting this on a full screen mode, sir?
Yeah, please. It's okay now?
Yeah, thank you. Yeah.
Yes, sir.
Yeah. So My specialization is cybersecurity, digital forensic, and I slightly moved on to the blockchain side. Quantum was not which I worked on, but when I started working, because I was doing some research on my side on security and forensic, then 3 years back there was something, and when I was just reading some research paper and I came across the Grover and this Soar algorithms. So that was something which was very interesting and challenging. So anybody who's working on the cybersecurity and related domain, they cannot avoid quantum, because this is something is a bigger threat for all security domain people. So then after that I started working on that, and I slightly went inside and did little more work. So from there my journey started. Well, the basic objective of this talk is to give you a little idea that where quantum is creating threat for security, and what are the algorithms which people are working on to protect you from that kind of threats, and where is the challenge to migrate, what kind of problem we have for migration. And it's not so easy to migrate because there are many technical issues inside. So those challenges actually open a new research opportunity, and it will take time to get good results on those directions, and it requires some time to get mature on those fields. It requires a lot of analysis, performance analysis, design, and implementation. So there are a lot of work which need to be done, but there is no time. Why there is no time? Some of you might be knowing who already studied or might have read some papers. So I will explain those points, that why we lack time now, and then I will focus on some of the challenging issues, and I will share one of my paper which I put on the preprint server, and whatever I am discussing on this PPT, most of the things have been discussed in detail in that paper. So this is the history where we started from 1981 and till 2019, and obviously from 19 you have a lot more things which has come across, and the development is continue. But if you see from 1981 till 1994 there was a gap. Again 1994 to 1998 you had a gap. Then 1998 to 2012 there was a gap. So the development it was not very what you say that continuous. There was some kind of, you can say that milestone. If we see 1981, 494, 98, 12, 17, 19, and now after that quantum supremacy, when it was proved, then many MNCs and even the many countries, they came forward to develop their quantum supremacy, and it's going on. What is the reason behind that? Okay, we will discuss that later on. So if you see that last 20 year, that how the growth has been taken. So 2019 Rigetti 128 qubit, and it started from IBM Oxford, with 2 qubit. So now what is the prediction? The prediction is, this is from the Gartner report, you can get it on internet. So you will get now in 2022, if you see here, we are on the era post quantum cryptography, where we will face problems. So by this we have some kind of quantum computing what you say resource which can break your algorithms, cryptography algorithms. But if you see from 23 onwards, prediction was 23, but exactly I can't say that it will work. Another 1 or 2 year you can wait, that will come. So from 23 onwards, if you see up to 2038, you have a lot of development, and we will see in future next 10 years that we will have some kind of system in and around of us where we will be using it for real-time works. So most of the things right now is going in lab and research organizations, but hopefully in another 10 years we will get it. So the problem started from Soar algorithms. So I'm not discussing the Soar algorithm, but anybody who is interested can get the research papers of Soar algorithms, and one is Soar and one is Grover search. So Soar algorithm, if you see, it is well proven that it will break your all the cryptographic algorithms in a matter of second. And if you see our current cryptographic algorithms, this is all based on the numbers prime factorization. So that is the biggest threat for all of. And then if something is not based on the prime factorization, then you have a Grover search, which gives a very good support for you can say that brute force search and brute force attack. So if you have a good database of passwords, and you can make all the combinations and find the best matching of the password and can break the algorithm. So both the Soar algorithm and Grover search algorithm, both the algorithm is threat for us. So if you just see the performance wise, so what is the efficiency? How extreme is the quantum speed up? So it is super polynomial quantum speed up. And if you look into this, I don't have pointer here. Okay. If you look here, number of bits which we are using today, 1000 to 4000 bits which we use for RSA encryption. And if you see the orange color line, you have blue color. So blue is for classical efficiency and the orange is for quantum efficiency. If you see the quantum computing algorithm efficiency, so after 1000 to 4000, if you see the time required computational complexity, it is almost constant. Whereas if you see for the computer classical efficiency, it grows exponentially. So what problem happens that even if you increase the size of your RSA key, even goes for 4000 to 5000, 6000, it is not going to help you. That algorithms will break it, and increasing the size of key is not the solution. So finally, it's proven that we are vulnerable. So if that algorithms is implemented, we are vulnerable. So someone can say that what is the problem now? Why it is not broken right now? So if I will tell you, if go back to the previous, to implement the Soar algorithm and Grover search algorithms, you need a quantum computers with million qubits capacity, which we currently don't have. So the prediction is that by 28 or near around that time, you may have. So you can see that 50, 300, 500, 1000 qubits. So we want million qubits. So million of physical qubits, which may exist in another 5 to 10 years. And if that happens, then your both the algorithms can be implemented. And once that is implemented, real-time system exists, then definitely your current RSA algorithms or your any other algorithms which is based on the factorizations, it will be broken. The point is what is the solution? So as I said that even if you increase the key size, it's not going to help you. So what's the problem now? So problem is that we have to move to some other alternatives which can be quantum safe. But there are a lot of work going on in that direction, which is quantum safe, but it has its own challenges. So I will just try to highlight those issues, and I will. Threats are like you have a public key cryptography, which you normally use for RSA signatures, and elliptic curve Diffie element key exchange. So this complete set of your algorithms are vulnerable to Soar algorithms, and there is no mitigation available. And another is symmetric cryptography, which is AES and SHA, which we use for various other purpose. that is vulnerable to Grover algorithms. So one set is a public key cryptography, which is vulnerable to Soar. Another set is symmetric cryptography, which is vulnerable to Grover algorithms. So Grover algorithms, I mean to say symmetric cryptography algorithms, whatever you have, for that you have some kind of way to avoid. So key size, if you increase, you can little relax. But for public key cryptography, there is no mitigation available. So that is the biggest threat. And unfortunately, most of the real-time applications which we use today, everywhere you are using public key cryptography. So the question comes that when development of quantum is still not completely realized, we don't know when this million qubits capacity quantum computers will come in reality. The challenge is that you can't wait for those days. Why? Because the research says that there are some organizations, there are some government agencies which is already recording your communications. They are harvesting these informations, thinking that tomorrow when this quantum capacity will be developed, they will use their techniques to decrypt those messages which is being recorded now, and they will decrypt in future to know what communication you are doing today. So that means that message recording or harvesting of your encrypted messages is already being done somewhere. So you are on threat. So you cannot wait for quantum computers to exist and somebody to break your communications. The threat is that it's already getting recorded somewhere, and you have to ensure that even if in future these quantum computers exist, no one should be able to break it in future. So you implement quantum safe algorithms now itself, so that even if it is getting recorded somewhere, there is no possibility to decrypt that in future. And that is the reason a lot of research is going on. And US defense agencies, NIST, and many other organizations have already given directives, particularly for defense projects and government organizations, vendors, defense vendors, the vendors who is developing software for defense organizations. So they have changed their strategies now, and they have given clear guidelines that what kind of algorithm should be there and what has to be replaced now, thinking that those algorithms should be quantum safe. So strategy has to be made now itself, and you cannot wait for another 10 years when the system will exist, because actual threat started the day the algorithm was disclosed that Soar or Grover search algorithms can exploit your communications or exploit your cryptography algorithm. So if from that day onwards, if somebody is recording your communications, and tomorrow if these algorithms get executed on these platforms, then your all communications are exposed. And that will be really difficult for particularly government organizations, because their all private communications will be exposed. So if you see that impact of these algorithms, and this is from NIST, I have taken, NIST is doing a lot of work on these directions to standardize the algorithms. So you have generic algorithms, which cryptography algorithm we generally use, AES, SHA, RSA, and electric cryptography, DSA. So if you see these, the purpose of those algorithms are some is for symmetric key, some are for public key, and some are used for encryption, some are used for hash, some are for signature and establishment. So what happened that if you have the large scale quantum computers, as I said, that million qubits are required to implement that those algorithms, Soar algorithm and Grover search algorithms. So if you have those computers in existence, then these algorithms which you are using today need to increase their key size. But you look into this, AES and SHA, okay, you can increase the large key size, but RSA, ECDSA, like all elliptic curve cryptography and other finite field cryptography algorithms, even if you increase the size, it is not going to be safe. So no longer secure. So once that computer exists, so there will be no possibility that these algorithms can protect you. So known threat is what? You have to find out some way to devise a new algorithms and find out the strategy that how you are going to change from this existing algorithms to the new algorithms. So if you see the Soar algorithms, traditional public key crypto systems efficiently solve integer factorization and discrete algorithms. Any adversary who sniff and record a publicly encrypted communication would be easily able to decrypt it. And this is what mentioned here, communication harvesting attack. So this is a very known terminology in quantum security, that they are suspecting that your enemies or your adversary countries, they are already recording some communications so that in future they can decrypt it. If you see the symmetric encryption and hashing, again there also you have a problem. So you have to double the size or you have to increase the size to mitigate the this problem. So what are the threats? So if you see, most of your current applications which you use in everyday life, like your virtual private network or your email communications or your SSL or TLS, then XML web services, public key infrastructure, then mobile app distributions and blockchain applications, these all are vulnerable. Everything will be vulnerable. In fact, the blockchain, if you see, the security of the entire blockchain is based on your public key and private key. The parties are signing their transactions and then you are hashing it to Merkle tree. So, okay, hash will not be the problem. Merkle tree will be not compromised. But when you are sharing your key, because the wallet and the transactions all takes place through the public key. So having the public key, if they try to do some reverse engineering, reverse engineering sense, there's a different strategy, but yes, it can be broken. It will, with quantum computers, you can break that. So if that happens, even your blockchain infrastructure, which you are building now, thinking that it is a very secure system, will be vulnerable completely based on this kind of system. So again, there you need to find out the strategy that how we can implement a quantum safe algorithms for signing purpose or generating a public and private key so that it will be safe. The problem with the blockchain technology, if you see, those who has gone through the blockchain, already blockchain is a very resource intensive process. And if you see in the blockchain inside, scalability is already a big challenge with the blockchain. With existing elective code algorithms and other existing normal cryptographic algorithm, you are facing the scalability problem with blockchain. Imagine if you use quantum safe cryptographic algorithm, what will be the issues? So all these things are giving a big threatening to us, that how we should change our system so that the changes will be very smooth, or else it will give a sudden shock, and changing the complete thing will not be easy at that point of time. So post quantum, what we will face, so there are two things which we can do. One is post quantum cryptography and one is quantum key distributions. Quantum key distribution is a separate things. It's already exists and people are using it. That is basically used for key distributions, but that is not the problem for us. The problem is post quantum cryptography. So post quantum cryptography is, you need to have some kind of algorithms which is very difficult to break even using a million bits of quantum computers. So there are various set of algorithms which is being developed, getting tested, and feasibility studies are done to identify that which algorithms will be best. So in that, NIST effort is remarkable. If you see that entire development of quantum safe algorithm, NIST's algorithms or their effort is one which is clearly visible, because they started long back and they are in third round, and many algorithms have been shortlisted, which is potentially a good solutions for post quantum. So these are the 5 categories which they have identified: the hash based, code based, multivariate, lattice based, and isogenes. There is a very good YouTube video. If someone is interested to know how these cryptographic algorithms works, I can just tell you that was RSA 2020 symposium, where all these algorithms has been presented with animated video. So you can search and see that what are the difficulty level of these algorithms, and what is the what is the security aspects of these algorithms, why quantum computers even cannot break it. And these algorithms are really very difficult to understand, because all these 5 different algorithms are based on 5 different techniques of mathematics, and it will take long time to understand each one. So if you go through those animated videos, it will give you overall understanding that, okay, what is the difficulty part on these algorithms, and why even quantum computers will take a lot of time to break it. So okay, you can search and see that. But now if you see lattice-based cryptography, it has been already proven that it is quantum safe algorithms. Even multivariate cryptography, there are many algorithms which has been developed based on the multivariate cryptography, which has been proven that it is quantum safe. So these 5 techniques which I am talking about, hash-based, code-based, multivariate, for all these you have, like it's already mentioned, that Merkle signatures, then McLeese, then multivariate quadratic, NTRU, and SIDA. So these are the implementation which is already done based on these algorithms. So these algorithms exist based on these techniques, and this has been proven that these algorithms are quantum safe. But the problem is that it is not only we need quantum safe algorithm, we have different issues, and that I will discuss in next few slides. So if you see that post-quantum cryptography algorithm, you have hash-based, multivariate, code-based, and some are good for the signature purpose, and some are good for encryption and key exchange. So code-based and isogeny and lattice-based are good for encryption and key exchange, whereas hash-based and multivariate is used for the signature purpose. And these are the known implementation, means the algorithms already exist. Even someone can download it from the Open Quantum Safe project. There is a website where already their open libraries are available. And a lot of research work is going on where people are using these algorithms to do the feasibility studies. So most active field of research and several implementation available for NTRU, Haber, and Frodo and signature like dilithium, Bliss, and Tesla. These algorithms are good implementation wise and feasibility wise, it's good, but it has its own pros and cons. Those pros and cons I will highlight now. So what is the problem for Pkc migration? NIST standardization effort is aimed squarely at the problem of determining which cryptographic algorithm are robust. So we have a set of algorithms which is robust, but the problem is not robust. The problem is how you are going to implement those algorithms on your platform. For example, today you are using a mobile phones, and the algorithm which you are talking about, which is quantum safe, even your MacBook will not be able to execute in a feasible time. And it is not only the MacBook. When you are suppose you are logging into Facebook, and when you are doing a bank transactions, so you need the communication in fraction of second. So for example, when you have entered your username and password to do the bank transactions, at the server end there is a time to leave, or there is a threshold value that how much time they can wait to receive the packet from your side. But if your system is taking more time to encrypt the packets or sending the packet to the server side, so it is not the network problem, it is your algorithm problem. If the time has increased, now you have to increase the time on the network protocol also. Otherwise, the packet will be discarded because it has taken, delay is more. So it is triggering the problem in various sides. It is not only that developing a algorithm which is quantum safe. I developed the algorithm which is quantum safe, but the time complexity is so high that all the other algorithms is getting affected because of that. So I have to change in the network protocol. I have to change on the router side. I have to change on the application side, every side. So it cannot be done in 1 or 2 days. the changes has to be done in a very systematic manner. And for that, you have to do a lot of research, because in all the quantum safe algorithms which we have gone through, I will share with you, all the quantum safe algorithms has a lot of variations, and there are so many permutation combinations of key size and the time complexity. So which algorithm will take how much time and which size of key is best suitable, that has to be tested exhaustively. Unless until you test and find out the best possible permutation combination, it will not give you the correct solutions. And for that, all you need to have you need to spend a lot of time to do the research. And the thing is, till now, even after 3 to 4 years of exhaustive research, NIST itself has not given the final output that which algorithm is the best. That means there are many things yet to be done, yet to be evaluated, and then something will come better. So, well, I will move on and talk a little more about that. So you see that as an illustrative list of key cryptography applications, like you have PKI, key management, authentication. So for all these real-time applications, you need to have algorithms which will satisfy your requirement. But keep it in mind that all these algorithms is not only based on your cryptography. Cryptography is one part. You have dependency on other hardware and communication protocols, which has its own constraint. So just changing the cryptography algorithms will not satisfy your requirement. It will trigger many other places. So the extensiveness of public key cryptography usage across the internet means that an industry-wide migration to quantum safe cryptography standard will be massive. And that is what the biggest challenge for us now. So what is that? While the realization of scale quantum computing may seem a distinct concern, there are some important reasons. And you, as I already told you, that uncertain QC development timeline, we don't know when exactly that actual quantum computers will be visible in and around us, and when industry and academia will start using it. Complex PQC migration requirements. So we don't have exact strategy now that how we will by manner to change it. And the third is record no exploit letter attack, which I told you that there is a discussion that many organizations and agencies are already harvesting the secured information, thinking that tomorrow when they will have the infrastructure, they will break those communications. So you cannot sit idle to wait and see when quantum will come and then I will change myself. Your threat started from the day now itself. So you have to implement today itself. So the research challenge focused on two different domains. One is core PQC migration research, and you have to find out the cryptographic agility. So agility, that again, I will discuss on now. That first we will talk about the migration challenge. So you need to have a very good research on that to understand that which kind of applications require urgent migrations and which kind of applications you can do some other alternatives. For applications which you need urgent migrations, you have to make the strategy and upgrade it. I will tell another problem. For example, if you are talking about defense applications, so defense applications which you deploy today may work maybe in the existence for another 10 to 15 years. But the processor and the memory which you are fitting now, after 5 years, if you want to implement quantum safe algorithm in that, the system may not support it. So you have to make your strategy today that we have this kind of threat, and for that threat, what should be designed so that in future, if you want to migrate it, it can be done easily. So strategy has to be designed right now. It cannot be tomorrow. So if you see that charting implication across domains, so these are the algorithms I told about, the 5 different types. So hash-based, lattice-based, code-based, multivariate, and super singular elliptic curve. So you see these algorithms are giving you these functionalities like digital signature, KEM, that is key encapsulation mechanism, digital signature, and these are the examples algorithms which is already existing based on these algorithms, these techniques. And their notable attributes is very important to see here. For example, if you see XMSS, This is an algorithm which exists based on hash base. So it is well understood, a stateful scheme, but needed to reduce large signature size. Most of these algorithms has very, very large signature size and huge memory consumptions, because the whole algorithm is based on mathematical toughness, that how your computers will not be able to break in a feasible time. So you are developing the algorithm which is very, very tough mathematics equations to break in. And that calculations takes lot more memory consumptions and CPU cycle, which our existing system, and even in the future when we implement, we have to think that how those system will support it. So large key size, you can see 1 MB, 11 KB, and very small size, if you see for KEM, which the psych, which is a implemented algorithm based on elliptic curve. So very small key size, 500 bytes. And some of the algorithm have a key size of 1 MB. So it's key size of 1 MB, you can imagine the difficulty level of those algorithms. I will just show you one of, I was talking about my paper. So I'll just share that. All these, whatever I'm discussing, a complete analysis part of that is shown on the paper. It is put on the preprint server, so you can freely access it. I will switch to that screen for a few minutes. Just a minute. Is it visible?
Yes, sir, we can see it. Yep.
Yeah. So this is the paper. I will put in the chat box so you can download there. You can read in your comfortable time. I have shared it. And yeah, so what I wanted to show you, see this. I have given the complete brief of any beginners also can go through it. It's a long document, 37 page. So what I wanted to highlight here basically that NIST has classified the 6 different domain that, as I told you, 6 different categories of cryptographic algorithms. So you can see that algorithm name and public key size and private key size. So the size of these keys in bytes are very, very large. And they take a lot of memory and CPU cycle for generating the key or verification of the signature or encrypting the data. So if you look into that, key gen per second and encapsulation per seconds, then decapsulation, and then algorithm memory consumptions. So these consumptions are very huge. And that is real challenge for implementing it in our existing system, particularly the small handheld device or IoT systems or smartwatch or your smartphones. So we have smart TV, smartphone, smartwatch, and so many other IoT devices, and particularly industrial control systems where the smart devices are small and they don't have that kind of resource. Even the existing algorithm is difficult to implement on it. Think about these kind of algorithm implementation on those devices. So you are actually on a big threat and you have a big challenge to solve. Okay, so I'm not going in my paper now. I will just quickly summarize because my objective was to give an idea that where we stand with the quantum computers security challenge. Okay, just a minute. Okay, so it's visible now. It's visible now. Hello.
Yes, sir.
Yes, we can see it. Yep.
So performance challenge is you have a large key size. Okay, I will make it full screen. So you have a large key size and you have more complex algorithms and computation is required. Security challenges, most of these algorithms, their memory and power consumption is very different. Need to analyze side channel attack also, that how this hardware analysis can reveal the patterns and can be broken. So that analysis is again different type of challenge. Then another area is that you have a variety of protocols, research needed on threat modeling. Then you have to do some different kind of crypt analysis. And as I already told that you have to do side channel attack analysis, which is again open questions. Implementation challenge. You have a very different kind of devices, starting from your smartwatch to smart TV to IoT device, which already have a lot of resource constraints. So how these algorithms will fit into that and solve the security problems is a big challenge which need to be solved. Then migration framework, what strategy you are adopting, which domain or which applications need to be migrated first to safeguard. That strategy has to be made. Obviously, in the government level, a lot of strategies required, particularly for defense and space organizations, where threats is very different. And whatever you develop it for next 20, 30 years. So once you built it, again, changing or upgradation will not be so easy. So what is the other approach? I'm not going in this detail. You have a hybrid approach. In hybrid approach, what research is going on that they are giving an option where you have your own existing algorithm as well as a set of quantum safe algorithms both. So based on the requirement, you are switching to the algorithms and doing the job. So the best strategy is today that if you cannot migrate completely, you add the quantum safe algorithms in your existing systems and slowly you try to migrate. And obviously complete migration suddenly is not possible. So hybrid approach is what gives you feasible solutions. Someone can go to this Open Quantum Safe org and you can see the performance of all those algorithms, which those algorithms are potentially quantum safe algorithms, and you can realize their actual key size and runtime complexity, memory complexities, and that will give you actual insight that what challenges these algorithms may pose if you really go to implement it. These organizations, I did a lot of survey and I found NIST-1, which is clearly visible and far ahead in these directions of standardizing the quantum safe algorithms. ETSI, ANSI, and there are one or two other organizations which is also doing some work, but the documents are not so visible in the public domain. Most of the document which is visible from NIST only. I have used these references to make this PPT. And what paper I shared with you, for that I have given around 60 references. So you can get a lot of information from that paper. So that's it. If you have any questions, you can ask now. Any questions?
Sir, so far there are no questions.
Okay.
Pradip, we do have one. Okay, I see it on in chat. So Dr. Manish, it is from Senthil, who wants to know that for real-time applications, is there specific choice in post-quantum crypto algorithm?
Real-time application, can you repeat the questions once again?
For real-time applications, is there specific choice in post-quantum crypto algorithm?
Yes, there is a specific choice, and that's what I said, that whole research is which algorithm will suit you best, because as I said, there are a lot of permutation combination possible. So there is no straightforward answer that which algorithm will suit me best for which type of applications. For example, if it is a very small IoT kind or mobile applications, and if you go for what you say that hash based this algorithms, those algorithms which has a large key size of 1 MB will not suit your requirement. Even with all permutation combinations, it consumes a lot of memory and CPU cycles. So among those 5, and I already said that openproject.org, where you can see for different kind of architecture, they are showing the performance of those algorithms, and based on the performance, you can pick up the algorithms which will suit for your hardware architecture or the platform where your application will actually deployed. So it requires a lot of analysis, and you have to very carefully choose the algorithms. And again, I am telling that still cryptanalysis and other research has been not done on those algorithms. So how safe those algorithms will be in future, it is still a question mark. So a lot of work has to be done. We have moved partially, but challenges are still there.
Thank you for the response, sir.
Thank you. I thank IEEE for inviting me in this session. Thank you.
Thank you for such an informative session, sir.
Thank you.
We are now elated to have with us Reena Dayal, who is the CEO and partner at Benzidine Advisors, a steering committee member of IEEE Future Directions Quantum Initiative, a member of Quantum Consultative Committee for the Government of Telangana, a founding chairperson for IEEE Special Interest Group on Quantum Computing India. She is also a senior IEEE member and a founding member and member of governing board of the Cloud Computing Innovation Council of India. She is a founding member of the former Chevening Alumni Association of India and a past chairperson for Storage Networking Industry Association of India. A certified corporate director and member Institute of Directors. She has several patents to her name and has also authored the book Innovation Magic, The Science and Art of Innovation Management. She is a Chevening Fellow for Rolls-Royce Science, Innovation and Policy Leadership Program, Oxford alumni. She is associated with Tata Group Executive Leadership Program, Ross School of Business alumni. Welcome, ma'am.
Thank you. Thank you for that introduction. And my apologies for not being there for the earlier timing of the keynote session. But I'm very happy to be here. Thank you for inviting me. And, it's so great to see so many discourses and discussions happening around quantum technology today. And it really reflects the vibrancy of what quantum stands for today. I mean, if I look back 2 years ago, there were very few discussions that were really happening, although IEEE has led that initiative right from the beginning. You know, when I had first recommended that we do a special interest group in Hyderabad, which was more than 2 years ago, I think it was very welcomed and very immediately support was given. And then, of course, Bangalore also very quickly, people got very excited about working in quantum. And then we got associated internationally with the IEEE Quantum Initiative. And they are very happy with the fact that India, in India, we are focusing so much efforts from an IEEE perspective on quantum. But today, a lot of discussions are not just happening within from an IEEE perspective, but there's a lot of activity happening both from the government side and the private sector, as well as if you look at startups. And all this is scheduled to become even more prominent. One of the roles that I do play is, apart from my IEEE association, I'm also the founder and chairperson for the Quantum Ecosystems and Technology Council of India. And the main objective of an entity like that, it's a not-for-profit entity, which is focused on incubating, enabling, and accelerating the quantum ecosystem in India. And, we are associating with the government, industry, academia, startups, every member of the ecosystem to see how we can support various initiatives that are happening. So from our perspective, from a QETCI perspective, if anybody is succeeding in India in quantum, it's our success. So that's how we measure ourselves. Everything that we're doing should be in partnership with somebody, because we are supposed to be helping somebody or the other. So that's the objective that is there. Now, I know that there's a lot of discussion that has already happened and is going to happen for, on very specific topics. what I'm going to do is to take you guys through a very, very high level overview of why quantum and what are the areas of focus I believe that we should be looking at from an India perspective. Just let me know when you see my screen. Give me a second. Are you seeing the slideshow now? All right.
We can
Yes,
see
ma'am.
it.
Yeah. So, you know, in this meeting, I don't want to talk about why quantum in the sense, not about what is quantum, but why quantum and why right now. So very briefly, I'm going to skip the slides on what is quantum. I think everybody knows what is quantum by this time, everybody who's attending. But I do want to give a little bit of a background of where quantum fits in the whole technology industry right now. We know that our current classical computing is based on semiconductor technology, and as semiconductor technology has evolved, we have been able to miniaturize classical computing circuits, increase computing power and capability, and you know, we've sort of seen this evolution where from very large mainframes we now have computing at our fingertips in our palms, right, with very small these phones, mobile phones, and many of these smartphones actually have more compute power in that small piece of hardware than the some of the early first computers that came into the picture in the first couple of decades. So I think we've seen phenomenal progress as an industry on that front, but we've sort of reached a plateau in the sense that last year TSMC announced breakthroughs for 1 nanometer technology, just moving from 10 nanometer to 1 nanometer to 5 nanometer, 7 nanometer, and 1 nanometer. All of that has taken a lot of effort by the semiconductor industry. And at the end of the day, the question that comes up is what happens after this? You can't go miniaturize any further because you start getting into quantum effects at those smaller distances. So what is the next generation of technology that is going to help us? Now that we've stage, you and I may ask this question, but in reality, people in the industry have been looking at this question for a couple of decades now as to where the next generation of computing is going to come from. And there's a lot of work happening in different areas like neuromorphic computing, molecular electronics and chemical computers, where chemical reactions are being used as a basis for computing, quantum computing, which is what we are discussing, DNA-based computing, which has found to be much more useful for long-term storage rather than compute, artificial organic brain or wetware computing, where people want to work with bio-inspired systems along semiconductor terms with semiconductor and looking at hybrid solutions. Out of all of these areas, quantum computing seems to be the most promising. And if you look as the next generation computing solution, and if you look at where most of the research is going, where most of the money is going into research, it's in the quantum computing space. So a lot of governments are now investing in this space. And this is definitely where we all need to focus our energies on. India needs to focus, is already focusing in this area, and more focus is required as we move forward. Now, I'm not going to go to what is quantum computing, but I just want to give a perspective of what it means when you're looking at quantum and where does the scalability come from. We say that quantum computing is going to create a exponential amount of computing capability, but exactly what does it mean? If you ask people, a lot of people are not able to visualize that. So I'm going to help you visualize that. So if you look at n bits, and if you look at classical computing, you can store any number in n bits between 0 and 2 to the power n, right? Now, given that we have something called superposition, in quantum computing, if you have n qubits, you can store all numbers between 0 and 2 to the power n. Notice the difference. Not one of the numbers, but all the numbers that fall between 0 and 2 to the power n at the same time, which means that if you want to look at the numbers that could be stored, if you had 100 qubits, we're looking at a quintillion numbers, right? 10 to the power 30. And then for 1,000 qubits, this is 10 to the power 301, which is close to what is centillion. It's different because we don't normally come across these magnitudes in day-to-day calculations, observations, and so on. And the scale is therefore definitely going to change. Now, if to put things further into perspective, if this is way larger than the number of stars in the known universe, which is in the order of 200 and something, right? So 10 to the power 200 and something is equivalent to all the stars in the known universe. And now we're talking about 10 to the power 301, which is way beyond that. So this is the kind of capacity increase that we are talking about. If you talk to the general public, right, and they will tell you, and you'll talk to a lot of business leaders, they will tell you that, oh, you know what, quantum computing is, I don't know how many years down the line, because we are still waiting for the scalable quantum computer. Next time somebody asks you that question, I would ask you to challenge them and ask, so what do you mean by a scalable quantum computer? What capacity, how many number of qubits will you call as a scalable quantum computer? And that question is important to ask, because if you have high fidelity qubits, just 1,000 qubits gives you exponentially higher capacity, as this particular slide is already telling you. And what does that mean? What this means is that when you talk about quantum security, and I'm so glad I walked into this meeting when the quantum security presentation Dr. Manish was making, because that is one of the most important areas I believe that we should be focusing on right now, not just in India but worldwide, because everybody is living in this cocoon where they believe that the day post quantum security will be required is many years down the line. 127 qubit computer is already here. There are roadmaps that have been prepared and shared by Google and IBM, which are very large companies, and putting a lot of money into this, where they are showing 1,000 qubit computer very close in 2 years. In fact, IBM in one of its roadmap had talked about 1,000 qubit computer in 2023. Now they might have revised that number, but we are not talking about a decade later. And this is what people can project. Actually, if there is a breakthrough in error correction in any of the known approaches that people are working on right now from a hardware perspective, then chances are that we will see the scalability much earlier than we had anticipated. And if you add to this fact, the fact that the post-quantum cryptography requires a lot of being able to address that requires a lot of upfront work for all the sensitive information that is being stored. It's not like a switch. Today you say, I'm going to turn on post-quantum cryptography. Because if you look at a bank, for example, banks have messy systems. They have mainframes, right from mainframes to some of the latest technology. They have a huge hodgepodge of different technologies in their data centers. And that means that the security patch-up that has been built for them also comprises of multiple multiple pieces of products, as well as a lot of custom things that are sitting around that. And within that framework, there is a security framework that has been built. So once you want to move to post-quantum cryptography, it's going to take a lot of effort. It needs to be handled as a proper transformation. So I think looking at where quantum is going to be, how soon quantum is going to hit us, I think people are just underestimating. There is a huge need to understand and focus on this. So one is quantum security, but then also focus on it in terms of trying to look at the power of quantum and use the various algorithms that are available to solve some of the industry problems today itself. And these need not be commercial industry problems only. These could be problems related to sustainability. These could be problems related to drug discovery, which directly impacts human health, and so many other issues in agriculture. And how do you make human life better? I think there's a huge amount of potential, and that's where the focus needs to start coming in right from day one. It doesn't have to be, hey, I'll wait for that great scalable quantum computer to be available, and then I'll start thinking how to use it. That's not how the industry is going to progress. That is not how the rest of the world is going to progress. So there's also a need to educate the end user industry a lot more. You know, in our own way, we are trying to do that, but whoever else can do that as well, you know, join the group, start spreading the message, and that will be very welcomed. Now, when we talk about quantum, there is another challenge. A lot of people just think of quantum as quantum computing. And of course, quantum, it's not just quantum computing, it's quantum communications. We're talking about quantum annealers, which are specific hardware and software solutions for solving very specific problems. If you look at D-Wave, D-Wave has a lot of quantum annealing hardware solutions, which are used to solve optimization, very specific optimization problems. And those are being used very widely. And then quantum sensors. You know, when we say, you know, quantum is tomorrow's technology, we forget that we've already been using quantum sensors for some time, you know, in different areas, whether it is for building better clocks, or whether we've been using it for some of the atmospheric sensors. And now, of course, gravity sensors, you know, sensors which enable space communication. There's so many applications, and this is not tomorrow's technology at all. There are breakthroughs that have happened in the last few years. There are very concrete industrial and defense applications that are being built around the world related to quantum sensors. So I think, and from an India perspective, there's a lot of strength. This is a Bangalore chapter organized session, and Bangalore IISc has a lot of quantum sensors based experience. So there is a huge opportunity for more startups to actually, you know, more startups to emerge in this region, in the sensing space. I think that's where people should be looking at, and we can have roundtables, you know, if required, where we can, you know, bring in experts from outside, and you know, do a little bit of a discussion around the kind of solutions, etc., so that right connections are established. Please feel free to reach out at any point in time if somebody's really thinking in that direction. Now, worldwide, if you look at quantum communications, India has been doing really well. We would all have heard the announcements a few months back about the progress in free space communication, and even, you know, we have a startup on the quantum key distribution side, QNU Labs, you know, which is doing reasonably well, and the situation is same or better across the world. I think every continent has its own focus on quantum communications, a lot of efforts happening in that space. Hardware also, there are multiple technologies that are people are focusing on for, and it's anybody's guess as to which one of this will result in a scalable quantum computer earlier than the others. You know, and India has a very strong background of photonics, so definitely I'm sure, you know, there's a lot more effort that needs to go in there in terms of finding a scalable solution. A lot of software companies, and I put these names here not because you don't know these already, you already know these, but I also wanted to share a very special perspective from a software scenario. And this perspective is linked to the fact that there are so many different hardware technologies that are being pursued today that let's say one of these technologies, superconducting qubits or photonics, makes a breakthrough. Now, we are also pushing people to say, start leveraging the algorithms for quantum at an early time, right? And I need to plug in. Start doing that. We are telling that to people, but at the same time, what is also happening is that people, you know, start looking at some of these technologies, and they start money into it, and the money is a small amount initially, and then suddenly some other technology makes a breakthrough. And as that happens, what's the investment that they have made in a particular technology? Now, many people, when they are deciding on investments, they're also realizing this aspect, and they realize this aspect early on. The software industry also realized this aspect. So what did they do? I think what many companies started doing, if you look at Microsoft, if you look at AWS, both of them have stacks which support multiple hardware. So what they're trying to do is to isolate the hardware variation from the end user community so that people can bet on quantum early on and they can start, using these solutions. And if the hardware changes, or some hardware becomes more prominent, these software vendors will take care of that problem. Now, this was one approach, and then of course we know that AWS and Microsoft both are focusing on some sort of hardware solutions also. But then there are other companies who are pure software companies like StrangeWorks and Classic Technologies who are trying to create a framework and give us, which is a software framework and APIs which people can use, where they're supporting all possible hardwares at the bottom. A Classic, on the other hand, for example, allows people to create quantum circuits, right? Model quantum circuits, which in turn get converted into code. And then, there's a lot of underlying hardware at the bottom. And people are, so these approaches that the industry is taking is very, very helpful for the end user industry to start thinking about using, working on quantum solutions without the fear of, what happens to my investment. Now, quantum annealers, of course, many of them solve optimization problems, which is nothing but solving the lowest minimum problem. And I don't want to, take too much time on this. A little bit about quantum sensors. There are geosensors, medical sensors for medical diagnosis, navigation sensors, material sensing, civil engineering, infrastructure projects, large infrastructure projects. When you do land surveys, etc., understanding what's happening 1 meter below the ground without really having to dig up, being able to do network synchronization, also being able to predict earthquakes and volcanic eruptions earlier because of having quantum sensors. I think there's a lot of applications in that space. I can talk about the use cases, but I'm realizing I'm already at the end of the session, so I would take a pause here and see if anybody has any questions. No questions? Let me read the chat.
As of now, we don't have any
Questions yet.
Okay, no worries. And basically, the last thing that I want to talk about is that the fact that there are a lot of industry applications which are already there for quantum, leveraging quantum. And this is not something that is going to, impact only one or two sectors. I think at the end of the day, there are use cases which are applicable to almost all the sectors that we can think of. However, because there are, some of the sub-themes within quantum are more developed than the others, the possibility of actually leveraging some of those areas is higher. So, for example, quantum chemistry is a highly developed field. And therefore, the applications of quantum chemistry for material sciences, for pharmaceutical industry, for chemical industry, all of that has a direct implication. And therefore, some of those use cases get associated with those industries as well. These are details of use cases not meant for this session. What I'm going to be talking about a little bit though is this. What are the other emerging considerations? So we have, while we've talked about some of the areas within, how quantum sensing is there and so on. Quantum artificial machine learning today, especially with deep learning systems, we've reached a sort of plateau. We've reached a state where the amount of money and effort that is required for some of these deep learning systems is so high. They require massive amount of compute for learning and also for the correlation. So in that kind of a scenario, we are reaching a sort of a plateau once again. And quantum holds the promise of creating this exponential, making a technology, computational power, which is exponentially higher at one level. But we don't have to wait for that. Already there is a lot of techniques that are being tried by people where, sometimes better classification is done through quantum, and then fed, this classical neural network is still being used. So a lot of permutation of combinations of AI and machine learning in classical and some aspects of quantum being brought in. I think that's something which is happening a lot right now with very promising results. The other area which is, is an emerging area is quantum biology. There are a lot of, this is not an area which is mainstream. It is very far from mainstream, but it has a lot of potential, and people are waking up to that potential. And, I believe, I've been talking about it for some time, and I do believe that there are some more efforts coming up in this space in India as well. Then, of course, quantum camouflage, because very good quantum sensors can create quantum radars, which can be a threat to other nations. If one country develops quantum radars, then the other countries, everybody needs to start looking at the aspect of quantum camouflage, right? So, and I think some nations around the world are already working on that. So I'll, pause here and see if there are any questions. And I can see a question: how do you foresee the quantum landscape developing in the future? I think there's going to be a whole lot more progress in the next few years, and we will see a lot more solutions in quantum sensors. Mainstream quantum computing, quantum AI and ML will develop a lot more. And I also believe that we will see some space applications, better understanding of the human brain as quantum computing matures, and lot of the other technology areas which are moving slowly will get accelerated because of quantum computing. This will also raise the question of ethics and governance principles around all these technologies. We already know that the issue of ethics and bias is a big topic for artificial intelligence. And as quantum matures, that topic will become more and more important. I think those efforts around the world will also need to accelerate in terms of, people ask me, why are you focusing on governing principles right now? And the answer is that, or ethics in quantum. The reason is that, it's not just about quantum, but the moment as we get better and better in quantum, we will escalate the risk associated with AI from a governance, ethics, or a bias perspective. And I think so some of those issues need to be addressed much faster. Then, of course, quantum will raise its own ethics questions as well, because of the exponential nature of the technology. So I see a lot more focus coming in there. We will also see society change, by the way, in terms of every time there is a revolutionary technology that hits us, we see the society changes, and we sort of reflect on it later as the general public, right? Just like the mobile revolution changed the way we lead our lives. Everybody is glued to their mobile screens, and obviously life has changed. Similarly, quantum is going to bring about several aspects of changes around in society. And cryptography, if you are somebody who's looking for where should you be spending where is your next generational leap in your career going to come from? So if you are a cryptography person and you don't understand quantum, please get to understand quantum. These will be some of the most highly sought after jobs in the next decade. People who understand quantum cryptography and who can actually solve the PQC problem, because everybody will be in a race to, become compliant and become secure, and so on and so forth. So with that, I hope I have answered your question partially. At least, how do you foresee the quantum landscape developing in the future? That's how I see it. Thank you.
Are there any more questions from the audience? Ma'am, I think there are no more questions.
All right.
Thank you so much for the informative session on quantum bits and quantum mechanics, ma'am.
Thank you. Bye-bye.
Our next speaker for today is Mr. Ruth Lineswala. He is currently getting his PhD in the field of computational fluid dynamics of hypersonic applications at the University of Minnesota. He graduated from Rutgers University in 2019 with a major in aerospace engineering and a minor in mathematics. At BQP, he leads the technical team and is focusing on emerging technologies and different areas to expand into. He's also actively looking at different kinds of simulations that can be integrated into BQP, along with advancements made in quantum computing. Welcome, sir.
Thank you. Thank you for the introduction. So I'm going to be sharing a presentation. Let me know when you guys can see my screen. Let's see. Can you guys see my screen?
No, sir, not yet.
Okay, let me try again. Do you see the PowerPoint?
Not yet,
No,
sir.
not yet.
Let me try this.
Yeah.
Yes, sir, now it's visible.
Yeah.
Great. Thank you. Thank you for the introduction. And so today I'm going to be talking about quantum simulations and specifically looking at the immediate and the prospective applications for different industries. Okay. So in today's presentation, I'm going to be talking about what is the motivation for thinking about higher computing power that's needed in the world, especially from the industrial point of view. Then the next logical step is the transition towards quantum computing. Then I will be talking about the near-term and the long-term applications. And the last will be some opportunities that from the industries, from the government bodies, as well as from the quantum companies, how everybody can come together for collaborations. Okay, so talking about the motivation, as you guys might be aware of, we have different sets of industrial revolution that has happened, going back to the 1700s, early 1780s. The first industrial revolution occurred, and that's when we started using steam power, and that was the first time when we started using other mechanical power rather than just human power. And then 100 years later, we got to the 1840s or 1840s, 1880s, where we got to the mass production. And that is where the conception of assembly line, the idea of assembly line and mass production really came into play. And that was actually popularized to the wide public by Henry Ford, where in 1913, they were able to produce 2 cars a day from top to bottom. That was a Model T, and his revolution of really associating or bringing in and introducing assembly line to the automotive industry went from 2 cars a day all the way to 12 to 14 cars a day. And for that, they have not only increased the production, but also decreased the value of the vehicle and making it more accessible to the wider public. And so the essence of this industrial revolution is really for helping out the community, the society, in essence. Now, going another 100 years, when we get to the 1970s, We have the Industry 2.0, where we have the introduction of computers and the whole aspect of automation. And so from that to the early 2010s, that's when we kind of go from, okay, we have now computer systems and automation, but now we want to kind of transition that into the whole aspect of creating the whole world in the cyberspace and introducing introducing a combination of cyber and physical space together. And now very recently, just a few years back, Industry 5.0 was actually introduced, where the whole aspect is kind of going back, taking one step back a little bit. And yes, we have introduced the cyber physical space, but now where the thoughts of the consumer really comes into play, and the customization of based on the users' needs is really playing it. Now, these are 5 different industry revolutions that has occurred. However, currently, vast majorities of different industries are actually stuck between Industry 2.0 and Industry 3.0, and that's what that's what Industry 2.5 is known as. And so the motivation from this point of view is really kind of taking a step towards the future and really taking one step towards relying more and more on the computers as well. Secondly, we have the whole aspect of digital twin, where we really want to immerse ourselves in the digital world, and this whole aspect of cyber and physical space really needs to come together, especially from an industrial point of view, where the testing, that's what's critical, is the testing is not only done in the physical world. Now it needs to change to a virtual world and quite literally be integrated within the physical world as well. Now, with this increased computing power, the needs for computing power, the logical way is that we have to go towards quantum computing. Now, why is that? We see that for Moore's law, as well as for Dennard scaling, there is an end, or we have reached to the end of both of them. Now, just to kind of describe you the Moore's law, it is essentially saying that we are doubling the number of transistors in a computer chip, in a standard size computer chip every 2 years or so. However, the size of transistor we are currently at is at around 15 to 17 nanometers. And we can only go for a few years until we get to the 5 to 7 nanometer range, from which that point beyond, we have to start considering quantum effects. Therefore, the Moore's law inherently in the next few years is ending. Therefore, if you want to increase the computing power, we cannot just rely on Moore's law or increasing the number of transistors we have on the chip itself. Additionally, the Dennard scaling, which is talking about the power density or how much power is required per given chip. And what we have seen is that even when we are increasing the transistor, or even when we're doubling the transistors every couple of years, the amount of power to power that chip, amount of energy required to power that chip, isn't necessarily doubling. It's kind of remaining rather constant. However, that is also coming to an end, where we have reached the peak efficiency of compacting our power density within a chip. And so from these two, we realized that what we've been doing for the past 30, 40 years, we cannot necessarily think along the same lines anymore. However, the ever increasing need for more computing power is always there in terms of the performance, as well as the accuracy and the efficiency that is needed from computing technology. And that is why we have to turn towards quantum computing. Now, to talk a little bit about the applications of quantum computing, the first one being the quantum-inspired approaches. Now, we don't necessarily need to transition immediately to quantum computing. I know Ms. Dayal went through several different applications, and some industries have already taken that steps. However, not every industry has taken that step. And the right way to think about it is to first go for quantum-inspired approaches, where these type of approaches are actually looking at the concepts of quantum mechanics and integrating those concepts into our traditional computing algorithms. And so we don't necessarily need these algorithms are actually performed on your regular CPUs and GPUs. They don't need computing quantum computers to be utilized. However, what we are using is the principle of quantum computing, such as superposition, entanglement, quantum tunneling. And so we're using that to go beyond from the traditional framework or the mindset. Now, looking at the current state of quantum computers, we have what are called the NISQ era, or the noisy intermediate scalable quantum computers. And in here, we have two different types of architecture, annealing and gate-based. Now, annealing architecture is usually provided by D-Wave systems. They're kind of known for it with 5,000 qubits. Their biggest system is about 5,000 qubits. And now for gate-based systems, we have various different ways to create a gate-based systems, whether it be from superconducting, photonics, or ion traps, and there are many other, such as neutral atoms and such, are coming up. But from gate-based systems specifically, what's important is the amount of qubits that we have, as well as the quality of the qubits and the gates. And when I talk about the quality, it's about the decoherence time, as well as the circuit depth that for which we can go. And what we have seen is that it's kind of like a seesaw, where if we increase the circuit depth, we cannot necessarily increase the quality of the bits, and vice versa, or the number of bits. Therefore, we kind of have to play around with it. And for some applications, the significance of the qubit count is so much so that when we are looking at really complex simulational problems, we need coupled bits, which we can obtain from ion trap and something along the. So is somebody saying something?
No, sir.
Okay. Okay. Yeah. So something that is superconducting computing, that's something that IBM, as well as some other companies are providing. They provide qubits which are not completely coupled. And yes, so they are quite useful. And we've seen that the number of qubits are increasing for such types of architectures, like superconducting gate-based architectures. However, for really complex simulations, we need those coupled qubits, qubits that can interact with each other, and not just the neighboring qubits themselves. Okay, so now talking a little bit about the specific use cases that people have looked at. The first one is actually looking at the quantum-inspired approach. And they've actually looked at the turbulent structure in a fluid flow and trying to mimic that using quantum many-body physics. Now, there's a lot going on in this example. So firstly, in fluid flows, you have turbulence, which is, by the literal meaning, is very erratic, unpredictable nature of the fluids, and that usually happens when the flow is not uniform, and that's the opposite of laminar. That's the opposite of turbulence. And so even though turbulence does not have any, cannot be predicted, we have over last 100 years, we have been able to define the structure itself. And we've been able to define the scales at which the turbulent structures can be defined. And so usually in traditional sense, what we do is we solve the equations of fluid mechanics are actually governed by Navier-Stokes. And so in order to fully resolve all the different length scales in turbulent structure, what we do is an approach called direct numerical simulations, or DNS. And so DNS is a very useful approach where in every single point in this entire fluid domain, you're solving your partial nonlinear differential equations, which are the Navier-Stokes equations. And so right now we can readily solve it using the DNS approach. However, that approach is incredibly costly that this when we're looking at a single fluid domain, we have to solve we have to solve these equations, the partial nonlinear differential equations. We have to solve millions of times per given time steps, and the time steps can be also going for thousands, if not millions. So you can grasp the bigness of the problem, how big this entire problem is. And so in this paper, actually, they simulated the structure by looking at the many-body physics that we have from quantum mechanics itself. So we're not readily using the quantum computing itself. However, we're using the principles of quantum computing in here. Now moving towards the next one, we have the quantum-inspired optimization. And we have several different approaches here. Let me know if you continue seeing my slideshow. You see the slideshow?
Yes, sir, it's visible.
Okay, great. So for the this quantum-inspired optimization, we have several different approaches. One of which is the quantum-inspired annealing approach. Now, the annealing approach is kind of interesting. Is that when we are actually going from one particle to another, when a particle can is wanting to transition from one state to another, usually in simulated annealing, they can only do into the neighboring or adjacent states themselves. However, with the quantum-inspired annealing approach, you're not restricted to the adjacent states. You can use the concept of quantum tunneling to go from one state to another, which might be completely on the opposite side of your state spectrum. So using this aspect, you're not very restricted, and you don't necessarily have to do every single state. You don't have to go through every single state, and that, as you can see, can minimize the amount of computations that is performed, therefore minimizing the computational cost, the time, as well as the resources needed to perform it. Additionally, if you, there's another approach called the PSO, or the particle swarm optimization. And so traditionally what happens is that this PSO, or particle swarm optimization, it's an, again, optimization algorithm which works on vector-based solutions. So to give you guys an example, suppose we have a linear-based optimization problem where we have to, suppose, minimize some linear system of equation based on several constraints of linear constraints. Now, so the answer we're looking at is a vector solution rather than a single point solution. And so for here, the quantum-inspired particle swarm optimization, it can, using the different aspects of quantum mechanics itself, we can go and perform much better than the traditional particle swarm optimization. And okay, now moving third onto the different types of problems that we are readily using on quantum systems. Now I'm going to be talking, going apart from the quantum-inspired to actually talking about the applications performed on real quantum computers. First one is in the automotive industry, where they're currently looking at, companies are actually investigating this to looking at the traffic flow simulation, and specifically for automotive is the ground-based system, looking at the traffic flow management, how the when, let's say, new roads are being developed, the proper infrastructure that is needed to make sure that the traffic is not that big of an issue, especially as we know in India, where the density of cars is really high, especially in major cities. And so this is quite critical. And readily people are, industries or companies are using that in the automotive industry. Likewise, in the aerospace industry, a similar thing is all being used, but in here we are looking at air traffic control. When we have incredibly high density airports, like we talk about, like Heathrow in London, or Mumbai's airport, there are so many aircrafts coming in every single minute. And so what they really want to see is how close two aircrafts can be within each other's range without one's fluid flow or airflow affecting the other. And along with that, when you are going around the tarmac, what is the most efficient way from the aircraft landing to going to the terminal and then depart again? And so you have so many different variables working here. And so that's why they're actually looking at quantum computing as a way to solve these problems. There are a couple of more examples in the chemical and the financial industry. I will not necessarily go right now just because of the time constraint, but if anybody's interested, I can go on later as well. Additionally, we have different types of here. We have the biological simulations and biological, chemical, thermal, and rigid and structural, flexible structural applications. And so from biology, we have the drug-target interaction, looking at how different types of drugs are interacting with the body and the body systems as well. From chemistry point of view, like Ms. Dayal already put out, it's quite an experienced field in the quantum computing right now. And specifically, they're looking at the simulating the molecular reaction and trying to find as efficient of a reaction as possible. And along with it, they're also looking at, with the whole new spur of the EV or the electric vehicle industry, what is the most efficient battery that they can manufacture in terms of the battery composition as well as the manufacturing process. And that kind of ties in with the thermal simulation, because as we've seen for the past couple of weeks, there have been many battery related issues in leading companies in India. And so most of them are due to the fact that there is a thermal runaway issue, or the batteries are overheating from whatever may be. And they're currently looking at how they can avoid it from the chemical composition itself point of view. And last one being the rigid and flexible structural simulation. The biggest being the crash simulation in this area. So imagine you have a car that you're driving and you hit a barrier. Now we want to create every single part, how the car will crumple, to how much your seatbelt will flex, as well as in what time your airbag needs to deploy. As you guys might know or might not know, some of you, but I think in the next few years there is a mandate that the Department of Transportation in India has actually instated that there has to be at least 6 airbags instated on all the passenger vehicles. And so now safety is really an issue, and performing these crash types of simulations, it is really important to ensure that these types of simulations are performed quite well. And so there is decreasing cost of physical testing as well. And we at Boson QSI are actually developing our software capability towards that. Okay, now talking a little bit about the long-term applications, we have I'm going to be talking a little bit about the growth of quantum computers, and with that, what it actually enables us to do. Now we have better and much bigger NISQ devices are being developed. As we know from, I think last October, IBM announces 123 qubit system, and like Ms. Dayal said, there is a promise of 1,000 qubit system by 2023. Sure, that might get that prediction might be shifted to 24 or 25. However, there are companies developing much bigger NISQ devices, and that is always helpful for for simulating such large and complex simulation types, increasing the qubit count as well as the fidelity of each qubits as well. Now, additionally, while that's happening, there is also the advances in the fault-tolerant quantum computers as well. And what that enables us is that it reduces the physical error rate to negligible levels. And so right now, it would be so that with our quantum error correction codes implemented with our fault-tolerant computers, the error rate will fall down to negligible levels, to essentially what our current computers will give you, traditional computers will give you. And now what this offers us is the increased complexity of simulation, performing much better, much more complex simulation, and much larger simulations as well. And to give you some examples, the one example that I gave you about the quantum inspired approach that's performed on our classical computers. Now, that's one type of example, but when you're looking at, let's say, from weather modeling, being able to predict the weather accurately with not just, let's say, a few days in the future, but if we go to a week or 10 days, that has implications on saving millions of lives when we're talking about extreme weathers of weather situation, whether it be from tsunami or earthquake or whatever it may be. And so these types of things are really helpful for predicting to saving millions of lives. Additionally, we have a lot of open problems in the aerospace where we have a transonic regime as well as hypersonic regime, and the cavitation, which is essentially the formation of bubbles inside some fluid. Most likely it's water. When propellers of a submarine are, propellers of boats are really spinning at much higher rate. There is actually a collapse of the water that happens, causing bubbles to be formed. And so that actually decreases the efficiency of the propellers quite significantly. And so it has implications on improving the efficiency if we know how to simulate that phenomena very accurately. Additionally, we have a couple system simulations. Something that I work on is the fluid thermal structure interaction. So you have three different physics interacting with each other. And like I mentioned just now, hypersonics is a very complicated field because you have so many different phenomena going on. And so having much better quantum computers, we can readily simulate such types of phenomena without having to fear about the computing power and the computational cost as well. Lastly, we have the multidisciplinary design optimization, or MDO. And so this is actually what we are, from the industrial point of view, what we are gearing towards. This aspect of digital twin that I hinted upon earlier, this is the type of things that we're going for, is that we want to increase the reliability of the different applications that we're looking for, but also how do different physics come in and interact together, and how can we design our whatever that the companies are looking to design, how can we optimize the design itself based on several different physics playing together. And so that is actually something that traditionally it's happening very, very rarely, and there are very many limitations right now with traditional computing, vastly coming from the required computing power from it. Okay, and so lastly, we have the lot of opportunities from, like I mentioned earlier, from the industry partnership, from partnership within the software and the hardware quantum computing companies, as well as from the government point of view. And so this aspect of hardware software co-design, it was actually introduced in the early 1990s, where they were looking at, okay, now that we have reliable hardwares, more or less, when we have the FPGAs, how can we design or create simulate softwares that are ideal for these types of applications? And that's kind of what's happening right now. With the spur of many hardware companies, more and more software companies are coming together, and we see some type of partnership being developed so that they can work hand in hand. Additionally, from the industrial point of view, there are many collaborations that are already happening, but we need more of these collaborations to continue to happen, to kind of propel us to the next stage, to kind of push us from this just quantum inspired or NISQ era approaches to thinking about much bigger systems, as well as going towards fault tolerant systems as well. And that kind of leads into the industrial quantum readiness that needs to happen from a lot of companies in the different industries as well, where they have to adopt quantum as part of their R&D process. And it's more of the quantum readiness is the key here, rather than expecting quantum to perform, or rather outperform traditional computing, is not necessarily the right way to think about it. It's more of, when we do go to a system, when we do get to a much better, much more efficient system, at that point, we don't want to be lacking behind. We don't want to then say, okay, we have much better quantum computers. Now let's see where we can try to apply that. We don't necessarily want to think about that. These are some of the things that I talked about today. And if you guys have any questions, I'm here. Thank you. Thank you, everybody.
Thank you so much, sir. We'll wait for a couple of minutes for some questions. Thank you so much for the session, sir. I don't think we have any questions so far.
Thank you.
Our next speaker is Dr. Kumar Gautam, and he is the founder and president of Quantum Research and Center of Excellence, as well as the founder of eGreen Quanta. He has a strong and professional education with a Doctor of Philosophy, PhD focused on quantum gate design based on Schrodinger dynamics from Delhi University, with an MTech from NIT Roorkela and a BTech from IETE Delhi. He has 8 years of teaching experience and has worked as an associate professor with a demonstrated history of working in the higher education industry with skills in MATLAB, quantum computation, Python, and other related areas. His mission model is focusing on quantum gate designs that are based on the excitation of atoms and molecules with electromagnetic fields. Welcome, sir.
Yeah, thank you so much. Good evening, everyone. So my slide is visible?
Yes, sir, it's visible.
Yeah, thank you. So good evening, everyone. Today I'm presenting just basic things about how to design a quantum gate or quantum computers based on discretization techniques. So there is so many programming techniques is there in quantum mechanics, but the people are more concerned about the some platform which already used like IBM or some QNN quantum neural networks and something. But here I'm just basic things. I'm just describing how to actually simulate through the any differential equations using the discretizations. So yeah, so quantum mechanics is a mathematical framework. So as a mathematical, so first you have to understand any mathematical equations, because all the differential equation is related to the quantum mechanics. So first you have to write the differential equation and convert or expand using the Dyson series, and then we can apply the discretization technique. This is the basic theory behind any programming of the approaching of through the MATLAB, because in MATLAB there is no any such library present in the quantum in the form of the quantum or anything like that. So how to approach, how to start the programming through the MATLAB, the basic things, because in India or in Indian student, everybody know about the basic things like the MATLAB or Python or C++. These are basic programming language. So I am here, I am just giving a small example related to how to write the programs and how to approach, how to start the process through the MATLAB. So as you know that the quantum revolution is not new from the beginning of 20th century. The numerous of groundbreaking technologies there started from the transistor to laser, and right now the people are talking about the some NMR, superconductive qubits, ion trap, many more other Rydberg atom. These are basically the system we can use and design the quantum computers. So quantum mechanics is the fundamental branch in theoretical physics, and which wide applications is experimental physics that replace the classical mechanics and classical electromagnetics and the atomic and subatomic level. First, you have to understand why we need basically the Hermitian operators. So in quantum mechanics, there is two things. One is operators, another is state. So we are just trying to using the Schrodinger dynamics in particular things, or Schrodinger interaction pictures, because if all the state are converted into Hermitian operators, and Hermitian operators follows the two conditions which satisfy the quantum mechanics. First of all, the eigenvalues is always real, and second is the eigenfunction are orthogonal. If eigenvalue is real, this is important because their eigenvalue correspond to the physical property of the system, which cannot be imaginary and complex. So Hermitian operators satisfy the first conditions. Second is all the eigenfunction are orthogonal, which greatly simplifies in the quantum mechanics. So we can approach the basic things. So first we have to write any of the quantum state in the form of Hermitian operators, and if you write the Hermitian operator, then you can start the programming through the basic tools through the which already in there in the MATLABs. So the quantum computers, the mechanics that perform the calculation based in law of the quantum mechanics, which is behave the particles and subatomic particles. They started from the Moore's law and in 1970 and to the 2020. And after 2020, there is many changes in the quantum computers. The people are basically designed the quantum computer based on the various platform language. Recently, the QNN, the one of the professor Bob's is the professor of the Cambridge University. He already approached some different approach, that is the quantum natural numbers. So this is the basic representation of the classical bits and quantum bits. As you know that the quantum computer which have not been built yet and would be based on the strength, the principle of the quantum mechanics, in which the smallest particle of the lights and matter can be different places at the same time. So in the quantum computers, the 1 qubits could be the both or the 0 and 1 at the same time. So with the 3 qubits of the data, the quantum computers could store all 8 combinations of 0 and 1 simultaneously. This means the 3 qubits quantum computer could calculate the 8 times faster than the 3 bits digital computers. So, in quantum computers, in quantum mechanics, so first you have to write the equation of the each state, and then we can define the state in the form of the Hermitian operators. So this is some computer languages there. Some of the basically the people are basically use some syntax like the QCL. This is the same C like that. QZCL. This is also, but these are just currently they are not specified, but specifications. They are just using this language specification, utilizing this same type of the C or C++ programming and for designing of the quantum computer, but not these equation, these programming language still not satisfied the fully of the quantum computers language. So first of all, the two type of the quantum software are there. One is a software running the quantum algorithm. The second is software enabling the quantum computer to perform. So the quantum software develop the kits like IBM has already designed the quiz kit, and the people are basically write the equation, and they are basically for the validation of the programmings we can verify through the quiz kit, and then start the coding through the quiz kit. So second is the quantum computer have performed issue due to the random error, and error correcting software is built to the correct such error, and the error correcting software as found in the low level programming that increase the stability of the quantum computers. So these are basically the software development that already developed by the some of the companies which already perform, and right now they are working on this. This is the Microsoft is using the likewise, and Google are using the they use the some platform and designing they are applying the and developing the quantum simulators. These are some companies basically they are using the software some recently right now, and the D-Wave, Rigetti, IBM, Google, Microsoft, Jepara. These are basically companies those are working on the quantum computers, and they have own software developers, and they are own software techniques, and they use that. And you can also validate your programs through these platforms. So some security related, the security depends only on the law of physics and not on the computational assumptions. These are also some they are might be possible in the next year, or might be very soon it will come in the picture of like a QKD or a quantum random number. That random number is already generated through the Cambridge professors, and some other might be possibly in coming year. The quantum digital signature is coming for the security purpose. Now, here I am what exactly I'm trying to basically define in a different way. I'm not using any such such any libraries. Not I'm using any of the platform of what exactly what exactly you have seen that. Here I am just I'm trying to utilize the basic things through the MATLAB in the MATLAB, and you can also apply these basics programming codes techniques and for the designing of the quantum gates like a Hadamard gate or a control gate or any of the gates. So as you know that the time dependent Schrodinger equation is everybody is knows about that equation is there, and you can just apply the Dyson-Series equations and expand that equations, and because the Dyson-Series expansion is in the form of integral form, and after that you can apply the discretization technique and develop that own coding and verify the performance criteria of the quantum systems. So this is a basic algorithm what exactly I proposed during my PhD, the control unity gate. This is the basic implementation. You can also apply that basic this technique. This is the tensor product of the x1, x2, x3, and applying that equation. And these are just random numbers, alpha 1, beta 1, beta 1, alpha. These are random numbers. The u1 is the one random numbers, and u2 is another. That two is the unitary states, and after that states are, as I told, that all states are valid for the Hermitian operator. So first you have to generate your own random numbers, and then every state behaves as a Hermitian operator. And this is basic things. You just apply the u is equal to u plus u star by 2. So you can apply that equation, and then next when you run the MATLAB codes, this is the basic result. So first you have to just convert all the state into Hermitian operator, and then apply into the basic equations, and you can see the results. What exactly you need. The basic things is you need for the quantum unitary gates. So all gates, unitary gate is basically that all diagonal elements are 1, and upper and lower triangular matrix are 0 and zeros. So this is the actual approach, and you can apply the Frobenius norm techniques. There is many optimization techniques there. One of the very simplest technique is a Frobenius norm. What exactly is shown is x star x of mod square is equal to trace of x star plus x. So x star into x. So you can apply here. This x is nothing but it is a ut, and you just expand the ut in the form of integral form and apply that ut into the x here and solve it. You can share the result exactly what exactly you need. Now this is I use that techniques, and as I told that this is the 3 bits 3 qubits. So just see that the 3 qubits means there is a 8 states. So you can see these are random number. You can apply these equations on the MATLABs, and this is the basically what exactly you need the equations. So 8 cross 8 matrix is there. So first this is the diagonal elements, and these alpha 1 rest 4 cross 4 matrix is you can just applying that solving the discretization technique, and get the value exactly what you need, and putting this value, and you will get that the unitary gate. And after that you can find the performance criteria, and this is the performance criteria of the any system that is an NSR. So you just NSR is equal to E, that UD minus UT ka norms by UD. So this is the error, minimum error, and what exactly use the desired. So division of the minimum error by desired gate, you can see the performance criteria. So all about the equations, what exactly I have seen, I have presented. This is the basic equations, and applying the this H naught plus epsilon Vt. Vt is potentials and H naught is Hamiltonian. Applying this and using the Dyson series expanding. So this is the simplest block diagram of what exactly I explained here. So this H naught plus epsilon Vt and this sum of is equal to total Hamiltonian, and this Hamiltonian you can apply the quantum Schrodinger systems after time t, because you are applying the discretization technique. So every time spent you are just discretize the random times, discretizing the time, and you get the minimum error through that. So UZ is equal to desired, and this is the UT is a given get. After that you can apply in this optimization technique. Here I use the provenience norms, and you see the minimum
Sir,
error.
the screen is
So,
black. Okay, never mind. It just came back.
yeah, not sure.
Yes, it's back.
It's visible.
Yes, sir. It's visible now, sir.
Okay. Yeah, it's visible, sir.
Yes, sir. Visible.
Okay. So this is basically the control gate model. What exactly we need that. So I am showing the simplest block diagram of the entire equations of what exactly I presented here. So this is the initial. You just generate the H naught. H naught is a basic Hamiltonian. That is a unperturbed Hamiltonian, and that H naught is equal to P square plus Q square by 2. Simplest. The P and Q is nothing but it's one of the state. Another is potentials. Potential. Another is momentum. So P square plus Q square by 2. So basic unperturbed Hamiltonian, and you can apply that equations into you convert into Hermitian forms. Another is perturbed Hamiltonian, and after that you can sum of these two Hamiltonian to total Hamiltonian. You get the total Hamiltonian HT. So HT is equation is equal to H naught plus epsilon Vt, and these equation you can apply into the quantum Schrodinger equations. So here you can apply and get the total equations, that is UT, and after that you can discretize. That discretize means that is you have to bound that equation, because if you are not bounding that, then it is not valid for the for our programming language. So why? Because the mod of V is equal to, we will get the infinity. So if any operators are infinity, then definitely will not get the unitarity. It is invalid for unitarity equations. So for after t is equal to t, so you have to bound that equations, and then we can subtract between the UZ. UZ is the desired, and UT is the given gate. What exactly you obtain from this equations, and applying that equations into the any of the optimized technique you can use. But here actually I used provenience norms, what exactly I explained, and you can see that gate error energy should be minimum, and that minimum is approaches to the unitarity. So our aim is to get gate error energy should be minimum. So if you get the gate error energy should be minimum, that means our desired equations is satisfied. So now I started the simplest equations designing. Here I am, what exactly I propose. This is this entire block diagram in the we are converting the mathematical form into first converting the block diagram, and after that we can apply the MATLAB equations. So one by one you can apply either simulating methods or through the coding. So in MATLAB there is a two method. Either you can simulate through the code, or you can also draw the each blocks. You can just pick the one H naught. You can drive this entire block diagram into simulating forms, and also we can see the run. You can run the equations and plot this. So this is the basically. So if people can try the hardware implementation, you can apply that block diagram into the hardware form, and you can see that the gate error energy also should be 0. But this is very difficult in simulating form. It is very difficult to get because we don't have any library, such library. So we are trying to create own library through these equations, and then we can draw the entire block diagram in the form of the blocks, in the form of the quantum gates, and then it will run. So I'm trying also. I did some blocks, some simulation, some simulating methods, and we designed the simplest Hadamard gate and as well as the control gate. Now I am trying to apply that entire equation into ion trap. if it will come, then definitely I will show you, and I can share the how to approach the ion trap or simplest. So, but here is you can see opt the simplest equations, like a simplest system is a harmonic oscillator, and after that we can go through that like harmonic oscillator. Then after that 3-dimensional harmonic oscillator. Then you can opt a ion trap, Rydberg atom, NMR, superconductive qubits, any, because what exactly we want? We want a Hamiltonian. We want any of the potential of the any of the system. If you have a potential of the any of the system, you can apply that basic equation and solve it through the addition series. And now here I propose the simplest methods, what exactly I explained. So implementation of the Hadamard, there is a mention already in MATLAB. There already mentioned the Hadamard keywords there, and you can apply, because in Hadamard gates we need equation is 1 1 minus 1 1 and 1 1 minus 1 by and total 1 by root 2. So this is a basic equation. You can run, and this equation you can verify that. Another is simplest method is like a Bell state proposed framework. How to define the Bell state using the Hadamard gate. So these two state are there. This is basically already given in the MATLAB library. We can opt that, and you can try. I will share this code to you also. Now another is what exactly this is the own. I have written this is the own code. You don't find any of the coding technique. This is the basic equations. What exactly you seen the differential equation, and now you can this differential equation. This is the one-dimensional differential. You can expand the one-dimensional differential equations. You can expand this differential equation using the Dyson series, and after that you can apply one by one. So initially we have to start the t should be 10. You can opt any of the time, and this is the basic things, and the determination of the t by t. And here is the UD is initially used just for the optimization purpose, initialization purpose. You can just choose the UD should be 0, and after that you can apply. This is the basic equations, because if you this ut is equal to e to the power minus I. This is the exponential complex signal. If you can solve this differential equation, then you can see that this ut is equal to e to the power minus I, and this whole term is ht. So e to the power minus I ht into ut. So this is the, you just see and just verify this equations, and then after that you can run these equations and see. Here I also propose the u1 and u2 that you already seen the control gate, and just run these equations, and you can see that the UC you will get that actual equation of the unitarity gate. This is the basic equations what exactly I try to use for the quantum gate, and using the discretization methods. So this is the basic forecasting, what exactly the many companies are, or what, how much actually the where you can utilize that. These are various areas where you can apply the quantum computing techniques, and you will get the result. And 2025 many more will be changed, and if specifically India is also more concerned about that, the quantum computing. And recently the people are more using for the quantum communication purpose, because right now the communication approaching the IIT Delhi and DRDO has already signed that the MOU, and they have a many opportunity. Even DRDO has given us many things, and even you can apply the simplest equation. So try to, it's my basic suggestion is that you can just write the mathematical form, any of the like quantum mechanics and just one dimensional or whatever that means, and that convert into the that mathematical differential equation into the discretization techniques, and apply the simplest coding techniques through MATLAB. And then after that you can verify that coding in the Qiskit and other whatever the platforms is there, and that see the what exactly the scenario is there. So this is the conclusion. What exactly I am presenting here, the basic view and content of the quantum-based informations, and some basically MATLAB tools is theirs, and very soon might be possible quantum libraries also will come in the MATLAB tools, and we can apply in the various application like quantum communication, Q distribution, quantum walk, quantum image processing, quantum control, even there are many applications there. So these are references. Recently, I have collaborated with some Australian startups, the Quaker, and I am also mentor of change of the Niti Aayog. And I recently I arranged a small workshop through Niti Aayog as well as the Quaker and QRace, and some MOU is signed by the SRM, BPIT, and ICBC. And one of the industrial collaboration is Entanglement Position. This is a UK-based company, and they have enough opportunity on the ion trap-based quantum computing. If anybody are interested or join with the basic coding technique through that, they can directly contact me, and let's start the work with that. Thank you so much.
So we have one question from the audience, from Mr.
Yes, sir.
Dibakar. How are random values of alphas and betas ensure Hermitian, if I understood?
Yeah, you can just check that. You can just generate the RAND rand or RANDN, any of the random number, just generate and apply that random number is like suppose x is equal to any random RANDN 2, that is a 2 cross 2 matrix. So RAND2 plus RAND2 is star by 2. So you can apply these basic things. You can automatically they generate the Hermitian operators. That means the two things we need a eigenvalues are real. So how will you get the eigenvalues real? Because we can apply the Hermitian operators.
So, thank you so much for the informative session, sir. There are no more questions from the audience.
Thank you so much.
I now request Dr. Prashant Mishra, Chair of IEEE Computer Society Bangalore Chapter, and also the Vice Chair of the IEEE Bangalore section, to provide the closing remarks.
Thank you. Hope I'm audible. Can you just acknowledge that?
Yes, you're audible, sir.
Sure. Okay. First of all, apologies in advance just in case my network starts fluctuating. I'm in a holiday location and I'm not sure how stable my network is here. But nevertheless, thank you for providing me this opportunity to speak in this symposium. I was following a couple of talks for the end, and I must say that the quality of the presentations and the content has been extremely well done and well received. Okay, now beginning with the fact that I am currently the chair of IEEE Computer Society Bangalore chapter, let me probably tell you a bit about CS Bangalore chapter and what are the things that we are doing under CS Bangalore chapter, and then probably I will speak about I will change hats, speak about what are we doing under industry engagement program of IEEE Bangalore section, so on and so forth, right? So a bit of history about CS Bangalore chapter. I am very thrilled to say that the chapter is in its 40th year of establishment. It was founded in the year 1982, and this happens to 40th year, and I feel extremely humbled to take up the responsibility of this very vibrant chapter as chair 2022. Now, our mission statement stems from the core purpose, which is to establish CS technical activities as the preeminent forum for innovation, information, and services in current technical areas, and to extend computing technologies and application into areas currently unexplored. So that's the charter of CS. IEEE Computer Society Bangalore chapter places an additional focus on fostering, mentoring, and supporting technical leaders, innovation, forums and platforms, interest groups within the Bangalore geographic area of operation, namely the state of Karnataka. So that's how the charter of CS is outlined, and that's how the charter of CS Bangalore chapter is outlined here. Okay. Now, this year, I think we have put forward an extensive list of activities and initiatives which we believe will immensely benefit our members, both students and professionals, either from the academic industry in multiple ways. Now, I would like to highlight the fact that the CS chapter is organizing 2 major conferences and also running a special track with IEEE Connect, which is a flagship conference of IEEE Bangalore section. So in IEEE Connect, we're running this track on advances in data protection and privacy. And I won't say it's a follow-up of it, but I think natural synergy is that we are organizing the 3rd International Conference on Public Infrastructure Applications, which is called PKI 2022. It is a joint conference between IEEE Computer Society Bangalore chapter and IEEE Industrial Application Society Bangalore chapter. This conference is happening somewhere in the first week of September. The CFP is already out, and I think the paper submission deadline will be towards the end of May. So I think for all folks, it's a call out to all folks in this particular venue who are typically who work in the area of security, data protection, privacy, cryptography, public key, and the applications and industrial use cases. I think this is a very good venue for you to come forward and publish your good work. The second conference that we're organizing this year is actually the flagship conference of CS Bangalore chapter, and this is something we will be starting this year. It is called the First International Conference on Data, Decision and Systems. It is called ICDDS 2022, and this is going to be an annual conference of CS Bangalore chapter for the from this year onwards. Now, as the title says, it essentially cuts across the theory of data and decisions, the systems aspects of it, and finally the applications aspects of it. So these are the three tracks we'll be running: theoretical foundations, systems, and applications. In addition to this too, and this conference happening in the first week of December, the CFP will be published soon, and the submission deadline is somewhere around the end of July. Now, in addition to these two major conferences, one on security and public infrastructure, and another on data and decision systems, we have multiple programs that we are putting in place for the benefit of members. And let me try to break that into different compositions and probably speak about it. Now, under the industry programs, we organize this flagship event called deeptech.ai. This year, the theme for deeptech.ai will be on e-commerce, logistics, and supply chain, which we believe is a very relevant topic, given that COVID hit us very strongly, and we are still trying to maneuver our way towards COVID. And this is a time where we really understood the power of supply chains and how well things can go right or wrong if you have a good supply chain or orchestrated for yourself, and how especially AI can be instrumental in trying to build robust supply chains. So that is one of the things that we'll do under the industry program. The second is the data, and probably this is something I'll come when I'm speaking about Bangalore section. Now, the second program is what we call for young women and women in computing. It is called Girl Geek and Girl Geek Hack. This program is specially targeted for young women who typically, we want to give the young women a platform to showcase their technical skills and also their implementation skills. I think this is a gap we felt that exists in the ecosystem, and this particular program called Girl Geek and Girl Geek Hack will address that. This has been running successfully for the last 2 to 3 years. This year, the theme for Girl Geek and Girl Geek Hack will be AI for social good. So stay tuned for that. Then under the standards program, of course, we have different types of orientation programs towards standards and standardization activities in computing. But we'll also run a very special track on women in standards. Now, the other initiative that we are running is the humanitarian initiatives program. Now, so the question to ask is that how can CS contribute to humanitarian initiatives? Of course, I think whatever we can contribute from a computing point of view that benefits humanity in a larger way, that is what we'll try to do. So under that, we'll be running this very focused symposium called sustainable.ai with a theme on green computing sustainability. So here we'll try to sensitize our audience to how we should apply green computing practices so that the type of computing algorithms and systems that we build are very, very energy efficient. So that's going to the focus of this particular initiative, and we will run it under the humanitarian initiatives program. Of course, under the university relations program, we have what we call the CS Connect, where we actually we have dedicated sessions with different universities and students and the student chapter chairs and faculty coordinators. But then this year, we'll be running what we call as the Student Congress of CS, which will again happen in the month of December, where we will try to pull in all our student branches and our student branch chairs and key office bearers and all different and students of CS to come under this single umbrella and talk about what they are currently doing. Then we run this program called Distinguished Lecture Program series, and the theme for this year is Celebrating Computing. So here we organize talks by very eminent people in the field of computing, and these topics are very, very focused and deep tech in terms of these computing areas they will be talking about. So keep tuned for that. This year we have put a number of awards and recognitions for our volunteers and our members. There were 2 awards that were running under CS, which was the Outstanding Student Volunteer Award and the Outstanding Student Chapter Award. In addition to these 2, we have added 4 new award categories this year. The first one being Outstanding Volunteer Award, second Teaching Excellence Award, third Research Excellence Award, and the fourth is Technologies of the Year Award, which is specifically directed for industry professionals. So I think the call out for 3 of these awards, basically Teaching Excellence, Research Excellence, and Technologies of the Year will be sent out in the month of May. Whereas the other 3 awards, Outstanding Student, Volunteer, Student Chapter, and Volunteer Award, will be sent out in the month of December. So please come forward and apply, because these are very prestigious awards from CS and CS Bangalore Chapter, and we would love you to become part of it. Again, given that this is going to the 40th year of IEEE CS Bangalore Chapter, we are trying to somehow journal the history of IEEE Computer Society Bangalore Chapter. So we have, in a way that we are able to document what has happened over this last 40 years in terms of who have been the key office bearers, what are the key initiatives did we run, what was the impact that the CS chapter of Bangalore bring about, and all these things we are trying to journal them. And hopefully towards the end of the year, we'll be able to come up with a small little journal of a couple of pages that will try to document this in a very interesting and intuitive manner. And finally, a call out is that, as I say, the chapter is only as strong as its volunteers members. So we would like you to, I would like to invite everyone to continue extending their support and contribute to the growth of the chapter, and feel free to reach out to me at any point of time in case you're interested to take part in chapter activities in some way or the other. And we are always looking for active volunteers who can come forward and spend their time with the chapter and pursue the passion in trying to do something good for the society through computing means. So this is me talking as the chair of CS Bangalore chapter. Now, let me wear the hat of the vice chair of industry engagements of IEEE Bangalore section. Now, under that, we have multiple things that we are doing. Let me start with probably taking the key from this current symposium. So the symposium that you are currently at, which is the symposium on quantum software, that's the first symposium that we have organized. There are 3 symposiums that will follow. The second one is going to be on drone computing somewhere in the month of July. And the very interesting part of this drone computing symposium is that we may, I think we may be also be doing a UAV competition in collaboration with the IEEE VTS chapter at that point in time. We'll keep you updated. The third symposium will be on digital reality. It will come somewhere in the month of September. And the fourth symposium will be on cyber-physical systems somewhere in the month of November. So these are the 4 symposiums. So one you've already attended, and so keep yourself tuned for the remaining 3. The announcement will be coming in due time. Along with that, IEEE Bangalore section and its DSS SIG, which is the Data and Storage Special Interest Group, in collaboration with IEEE Computer Society, has been running this very successful workshop series called Data and Storage Summit. We run 2 editions every year. This year we will be running the 4th and the 5th edition. So we run one in summer, somewhere in the month of June, July, and another month of November or December. So that's why I call it summer edition, the winter edition. And as you can understand from the title, it is about data and storage. So essentially, this is a call out to all folks who are very deep into storage and systems. I think this is a venue you should come and attend, because for the last 3 editions that we have done, the response has been immense. We have been able to pull in all the who's who in the field of storage and systems. And the proceedings has been extremely well received by the larger technical community of IEEE Bangalore. So please look forward to the notifications that come out for Editor Storage Symposium. Then there's another segment of activities that we do under professional activities. As part of that, we organize some of a monthly or a quarterly expert lecture series. So we are organizing a lecture series on the topic of space tech in the end of April. So stay tuned for the updates that are coming up in due time. And along with that, we also publish what we call as IEEE Bangalore Tech Icons. So here we try to recognize people, professionals especially within the academic industry, who have been doing especially good work in the field of technology, and we somehow try to recognize that in the by giving them this typical honor of IEEE Bangalore section tech icons, and we try to also take the interview and publish them online so that they can inspire students and young professionals by the learnings and the roadmap they have taken to become to come to the level that they are currently today. So stay tuned for the tech icons for this year. We have already recognized around 7 tech icons in the last 2 to 3 years, and this year we'll recognize another 3 to 4 tech icons. So stay tuned for that. The other initiative that we'll always running is the PhD summer school. This is a summer school that's going to be very exclusive for research students, masters with research, PhD students, and especially undergraduate students who are very passionate to make a career in research. So it's going to be a very exhaustive summer school, probably a week-long activities are being planned. Again, and I think the venue is going to be in ISC Bangalore, so stay tuned for the updates. And this is a call out for all young professionals or undergraduates, or master's students, already people doing PhDs. And we have carved this curriculum in such a fashion that everybody, we want to give you the flavor of how to probably bring an impact in trying to do good research. Okay, so please keep tuned for this particular summer school, and you will get the updates coming in a short while from now. Okay. As part of the larger industry initiatives, I think we run multiple activities. One of them is what we call as the CXO Roundtable. As the name suggests, it's basically a roundtable of CXOs of various industries, tech industries. We recently had one roundtable last month, which was extremely successful. And I think the way it was conducted, I think we found multiple avenues where a technical forum society like IEEE and industry can collaborate in a big way. And we could see mutual reciprocation from each ends in terms of the eagerness to collaborate, because I think, as you understand, this is a world where we live in ecosystems, and ecosystems are very meaningful because they help us to really scale well, because they try to augment each other's capabilities in a very positive manner. So I think this CXO forum brought that flavor out, and we'll be organizing probably 1 or 2 more editions of such CXO forums in a couple of our flagship events, which again, so stay tuned for that. In addition to that, I think the flagship event from the industry activities team of IEEE Bangalore section is what we call as the Bangalore Technology Conclave. This year, the theme of the Technology Conclave is Metaverse. I think this is a theme that we have taken up because there's a lot of buzz about Metaverse, but I think we still don't really have a good handle as to what to expect out of Metaverse. So I think we want to take up this theme and bring in speakers and experts who can probably sensitize or educate our members and audiences as to if a thing like Metaverse comes is in the making in the next few years or next few months. What are the things I think people should be trained in? What type of impact will Metaverse bring about? And typically, what will follow post Metaverse? So I think these are some of the things that we want to touch upon. And of course, what are the industry segments that will get impacted due to Metaverse? Okay, so be tuned for this Bangalore Technology Conclave. And we also run the IEEE Bangalore Industry Awards. It's a very exhaustive list of awards which tries to recognize individuals, startups, large organizations, teams for doing outstanding work in the field of technology. Again, the notification call for these awards will go out somewhere in the month of May. So if you believe that you have made some significant contribution in the field of technology, I think this is a shout out to all you guys to come forward and nominate yourself, because unless you nominate, we cannot take the application forward. So a big call out to you that please come forward, nominate yourself. You will be vetted by a very eminent jury, and if selected, I think there's a very well-designed recognition that IEEE Bangalore section has for you. So please keep tuned in for the dates and the awards that we announced, award categories that will announced very soon. Okay. So this was my brief about the industry activities of IEEE Bangalore section as Vice Chair. And I also gave you a brief about the activities that the Computer Society Bangalore chapter is planning this year, and some of which we have already taken up. So we look forward to your support in the best possible fashion, because as I said, without your support, without the support of volunteers and industry members like you, none of these programs can be actually put into practice, and more so we cannot scale and do an impact that is which exactly is the motto for which we all stand for. So with that, let me close my talk, and I'll pass on the podium back to the MC. Thank you very much. If you have any questions or any typical points you want a little more clarification on, I'm here. Please ping me here, or of course you can reach out to me over email. I'll be very happy to answer your questions. So thank you very much. Thanks for the time.
Thank you, sir. I would once again like to thank all the audience members and speakers for attending today's session. And I would like to inform that the recording of this entire symposium will be on the Bangalore section's YouTube channel.
Thank you, Praneeth, for moderating this session. We have reached the back end of the session. We would be calling it a day. As Dr. Prashant informed, please stay tuned for the further notifications on the rest of the symposiums from IEEE Bangalore section and IEEE Computer Society Bangalore chapter. Thank you once again, and have a good evening all.